Hello, everyone, and welcome to day 2 of virtual IoT and Edge Days. My name is Serena, and joining us today is our very own Frédéric Desbiens at Eclipse Foundation, who will be kicking off day 2 for us today. Without any further delay, Frédéric, over to you.
Thank you, Serena. And I'd like to acknowledge the great support of our marketing team at the Eclipse Foundation in organizing those 2 days of presentations. So, of course, Serena is the visible face there, and thank you so much, Serena, for your professionalism. And behind the scenes, there is Clark Rondy, my dedicated marketing manager in the marketing team, and the rest of the marketing team. So thank you so much, dear colleagues at Eclipse. So today, we start with my own presentation, but before that, let's review a bit our menu for the day. So right after me at 11 Eastern Time, we'll have a very interesting presentation on how Eclipse Ono enables you to migrate from Google IoT Core, which has been discontinued. So really looking forward to that one because I think it showcases the power of open source at work. Right after that, at 12:15 Eastern Time, we'll have our first ever Web3 presentation at Virtual IoT and Edge Days. And that will be interesting since, of course, your mileage may vary what you think about Web3, but certainly this is a trendy and interesting topic. So looking forward to see what our friend from IoTex will have to say about this. And then a presentation, going from Web3 to DTLS and very constrained devices with our friend Hakim Kraus. Hakim is the project lead for Eclipse California. He's involved in the tiny DTLS project as well. And certainly I'm keen to see his detailed technical presentation on the topic. And we'll close the day with a presentation on Edge Native architecture by Kilton Hopkins, the chair of our Eclipse Edge Native, and of course, the project lead for Eclipse IO Fog. So quite an interesting day. But for the time being, you're stuck with me in my short keynote on today. So let me share my screen and we'll get on the way. All right. So really, this is not a presentation about our extensive Eclipse IoT toolkit or anything like that, right? Of course, we have an extensive IoT toolkit at the Eclipse Foundation, but really the intent there is to discuss current trends and what I think about them, really. Now, I think I forgot to include my own little profile in the presentation, so we jump straight away to the content. So if you don't know me, let me introduce myself just in case. I'm Frédéric Desbiens. I manage IoT and Edge computing programs at the Eclipse Foundation, which means I'm taking care of Eclipse IoT, Sparkplug, and Edge Native. And I have the pleasure to work with 50+ open source projects in the space of IoT and Edge. So that keeps me quite busy. And so this first slide in my little talk here is really a fantastic perspective on what's happening here at Eclipse. Since 2011, we celebrated, already, nearly 18 months ago at this point, the 10th anniversary of Eclipse IoT. And when you look at this timeline of the main projects, not every project even is on this slide, you see, okay, the gradual, the growing wave of open source innovation in the space of IoT and edge computing at Eclipse. And we have one new project that's, getting close to get its code contribution done and all of that. That's Eclipse Tokandira, which is a historian database system that goes along with Eclipse Fortiac. And maybe there will be others this year. And of course, if you are working in IoT and Edge and are potentially interested in contributing technology to Eclipse, you can get in touch with me and I will get you through the process. This is fairly straightforward and most of the times painless. But this presentation is not about specifically our extensive toolkit. Okay, and this is another view of it with, the logos for the 20 to 25-ish most popular projects that we have. So my point here is to focus on 3 current trends that I personally saw in the ecosystem the last few months. And we'll take each of them, in detail. But really, the first one being that open source hardware is here for real at last, and this has tremendous implications on the open source IoT and Edge ecosystem. The second one being that open source challenges pay-to-play open standards, because for a very long time, there was one way of doing business around open standards, and open source is obviously challenging that at this point in time, and we will see together how. And finally, we'll discuss how open source beats unfocused commercial platforms. And the point of this third point here is not to say that commercial platforms are bad. Many of our members have commercial offerings on the top of open source projects that are built at Eclipse. Without those open source projects, we could say that those commercial offerings wouldn't exist, but the reverse is true. Without successful commercial products built on the top of those open source projects, the Eclipse Foundation wouldn't be able to support those open source projects and the open source contributors and committers that work on them. And so this is not about commercial bad, not at all. Eclipse is a commercial friendly open source community, but rather the fact that in IoT, we see that general purpose, unfocused, undifferentiated commercial platforms are failing right now. And we'll see that this is in fact great news for the open source ecosystem. Okay, so first, open source hardware is here for real. If you've been around in the industry for a while, you know that, custom chips are a constant in the landscape, and they have been for quite some time, especially if you are a device maker, picking the right ARM core or the right SoC and then customize the silicon a bit, working with your supplier. This is run of the mill, but all of that was happening behind closed doors, and you had to sign NDAs and licenses and things like that. Open source now is changing things, because you can have actual open source hardware, or we are very close to getting it. And a very good example of that is the Core 5 microcontroller, or MCU, from Open Hardware Group. If you're not familiar with Open Hardware Group, they are a kind of sister organization to the Eclipse Foundation, in the sense that we have a very close relationship. We are distinct corporate entities, you could say. But from an open source community perspective, we work very, very closely together. And the reason for that is simple. I mean, of course, hardware is very different from what we do at the Eclipse Foundation working on open source code. And so we don't have the technical know-how as a community to work as chip designers. And on the other end, people in the hardware community wanted to really push this concept of open source processor cores, and they didn't have the processors or at least the maturity in their community to do that in a structured way. So essentially, Open Hardware Group adopts lots of the processors and way of doing things of the Eclipse Foundation, in order to bring forward this open source hardware platform. And so Core 5 is a family of open source cores that leverage the RISC-V instruction set, because in the case of RISC-V, it's only the instruction set in the past that was really open. Okay, you could take it and build your own chips with it, of course. But if you weren't a chip designer, then, you were out of luck. And Open Hardware Group is pushing that logic further by working openly on GitHub on open source processor cores. So you can go there, download the system Verilog for those chips, those processor cores. In the case of the microcontroller, the full microcontroller source is there. And really, you can, implement it as is, or take an FPGA and run it on an FPGA and improve it, and then go to a foundry and get those chips made. But what they announced last year, and now the project is coming close to fruition, is really that they will be selling development kits with this open source microcontroller based on RISC-V at the core. And so you see the various technical features of the development board. It will have a built-in Ashling Opel ILD debug module, USB-C for terminal and onboard debug access, lots of interesting things. And of course, a few built-in onboard sensors as well. And so if you are interested in open source hardware, this is your opportunity right now. They have a campaign. They are taking names. If you want to get an early access to this particular development board, then you can do so by clicking the link on the slide. And of course, I will make those slides available, after my presentation. But really, the implication of this are really tremendous, because now you can do open source all the way from the microcontroller up to the full IoT stack in software. And when you combine what they are doing at Open Hardware, really working on the core processor IP and the tool chains that go with it, so proper versions of GCC and everything to compile your applications, and of course even a full-blown development kit, the Core 5 IDE they call it, and then you add on the top the IoT building blocks that we have at the Eclipse Foundation and specifically at Eclipse IoT, and this is a comprehensive open source RISC-V stack that you can deploy to support your projects and applications. And the value in this is not so much in the fact that everything is open source. Open source is cool and all of that, but there's no inherent business value in this. But really, the value comes from the customizability, the flexibility that you get in the whole solution. By having full access to the processor core IP, to the microcontroller IP, all the way up to the IoT building blocks, you can tweak things according to your own needs, and you're not dependent on any random program manager or product manager in order to do so. And this, is a tremendous opportunity, a tremendous possibility that's afforded to you. So I really encourage you. You can now, right now, buy the proper FPGA and run the Core 5 MCU on it. And this is something I've been doing for the last few months. But really, with the development board, things will be much, much easier for you. So I certainly encourage you to sign up for that if you are interested. Now, our second trend, how open source challenges pay-to-play open standards. So open standards, have been around for quite a while, but traditionally, they were working a bit like this, right? So you had to be a member of a foundation or industry group, and then depending on your membership category, you were getting access to the specifications and then some other ancillary things like sample code and things like that. So open standards, the old way, were really, they were built behind closed doors. So you had to be a member in order to work on the standards. And then you had to continue to pay a membership to access and use those same standards. And OPC UA is an example of that. I'm not saying that OPC UA is bad technology or that the OPC Foundation is a bad thing. But really, this is this dynamic where we are building open standards, but, some people have priority access because they are paying a membership in the OPC UA Foundation. And so this model means that this is not, a truly open community, essentially. And so the way that we are doing things at the Eclipse Foundation is a bit different. And the Sparkplug specification is a good example of that, in the sense that, of course, we are happy to get members, right? This is our source of revenue at the Eclipse Foundation, the fact that we have membership fees. However, in the case of Sparkplug, which is a specification that uses MQTT as a transport and brings interoperability to MQTT devices and applications, anyone can implement Sparkplug free of charge without being a member of the Eclipse Foundation. Anyone can use the technology compatibility kit that the Sparkplug team produces to validate that their Sparkplug implementation is conformant. And anyone can propose ideas or improvements without being a member. Sparkplug is built in the open in a public GitHub repository, and I put the link on the slide. And really, there is this dynamic where, yes, you can be a member and support financially the Eclipse Foundation in building Sparkplug, but everything that we do is in the open, okay? And this changes drastically the way that this community operates compared to OPC UA or older open standards that you would find in the industry, because we're not hiding anything. And really, right now, the Sparkplug specification team is putting the final touch to its release plan for the next release. And once we have done that, everything will be public. And of course, there were a number of outside people that already proposed ideas and improvements that are integrated. So if you want to do that, you just go to the repo, create an issue, and the specification project team will interact with you. And ultimately, of course, it's up to them to decide if they take you, if they integrate your idea or not in the next version. But you can do that and have a public conversation about things. And really, this changes the dynamics compared to older style open standards. So certainly, I think this illustrates the power of open source. And really, I'm excited to announce publicly today for the first time that not only we are working on the Sparkplug specification at Eclipse, but that we were successful in our proposal to make Sparkplug an ISO IEC international standard. And essentially, we submitted Sparkplug for that in November 22. There was a ballot of national bodies voting on the proposal from February to May. And the ballot closed a few weeks ago and was successful. So there was unanimous approval of the voting national bodies, the ones at least that took the time to vote, to approve Sparkplug as an international standard. So there are still a few steps in the process. This is not officially published yet. It would take some time, maybe by the end of this year, maybe a bit later, early next year. But in any case, Sparkplug will be known as ISO IEC 20237. And this is a tremendous achievement. This is the first time that an Eclipse technology, that an Eclipse specification becomes an international standard. Now, my third point about the fact that open source beats commercial unfocused platforms. And really, we saw a string of news in the last few months where Google announced that they are shutting down later this year their IoT core service. And IBM is doing the same to the Watson IoT platform. And even Microsoft, which has been fairly successful, with Azure IoT, or at least that's my perception as an outsider to the company, they announced that they are making fairly deep cuts in various groups, and several people in their IoT organizations were impacted. And this doesn't mean that IoT platforms are worthless. This doesn't mean that it's not possible to have a successful commercial success with IoT platforms. But really, this rather highlights the fact that if all you have is a generic IoT platform, not customized for specific verticals, not customized for specific use cases, that's just something that anyone could use, so highly generic, then you won't be successful. And we have a great presentation later today about how you can migrate from the Google IoT core service to an open source based platform. But really, what this emphasizes is that anything that's generic, anything that's a commodity, is better when it's built as an open source project, okay? Because you can fairly easily replicate with the Eclipse stack what you found in those various commercial unfocused IoT platforms, okay? So when something is a commodity, when something already exists in open source or could be built as an open source feature, it's better to do it that way. And then you can innovate in the commercial space, at the top of the stack, so to speak. And several of our members have value-added, focused commercial products that are successful. So my message to you is that if you are in the IoT space, differentiate by leveraging the great open source IoT building blocks that we have at Eclipse and elsewhere. I mean, the Eclipse Foundation is not the only game in town there, but really take the time to explore what's available in the market and then build your commercial product on the top of that. Don't reinvent the wheel and don't develop something that everyone else is doing. Join the effort, help us improve our great open source projects, and then keep development efforts to differentiate, at the top of the stack. And really, open source brings a lot of advantages to the table there. You can run anywhere you want when you are working with an open source platform. You want to run on the Google Cloud, you can. You want to run on Azure, you can. You want to run in your own data center or start your own cloud service, you can. This is really the ultimate flexibility. There is no lock-in in there. Of course, working in open source also means that you join a community, not a user base. And there's a tremendous difference between the two. When you join a user base, you are at the mercy of some random product manager somewhere that will decide whether or not the feature that you want and need will be prioritized or not. When you join a community, you are part of the stakeholders, you are part of the decision making. And this changes the dynamic a lot. Now, of course, there's no free lunch. So if you join a community and all you do is consume, then you don't get the full array of benefits. Really, you will get the most benefit of an open source community when you join it, when you consume the technology, yes, but when you give back as well. So when you have on staff people that are knowledgeable about parts of the stack, then other people will jump in to help you out eventually if you have problems with parts of the stack that you are not involved with. And really, this community aspect is one of the key advantages of open source. And finally, open source doesn't mean that there are no commercial products, okay? So if you need the support, you can leverage commercial products built on an open source core, or you can leverage the services of commercial companies that offer support for open source projects and products. And really, this, once again, gives you the flexibility. If you can do things on your own, you do. And if you need the support, then you will find it. And once again, this is about giving you the possibility to make the right choice for your organization. So what can you do if you are starting in the ecosystem, or even if you are part of it and all you've been doing is to consume the technology? So there's an easy first step that you can take in order to support the commercial, the open source projects that you care about, and that is to show your company as an Eclipse IoT adopter. So you go to ioteclipse.org/adopters, there are instructions there, and you can showcase your support for the open source projects that you care about at Eclipse. And the value of that is really important, because otherwise the open source project teams have no idea that you are using their code, that you are using their technology. And so if they want to, let's say, organize a meeting of stakeholders to discuss new ideas and things like that, they won't know that you are around. They won't know where to find you. So please show your support by becoming an adopter. It's a fairly easy process. And if you have trouble with it, you can reach out to me. Then, of course, the second step is start contributing. Contribute ideas, documentation, specifications, code, because that's where the most value will come out of your membership in an open source community. And this is distinct from being an Eclipse member. As I said, of course, if you become an Eclipse member, that's great, but that's not mandatory. And the third part is, to join our working groups and other initiatives. Everything that we do at Eclipse, including the other staffers that we have on the staff, we are there to offer support and services to our open source projects, to the actual committers and contributors doing the open source work. So by becoming an Eclipse member, you invest in this open source community and make sure that it will be around for 10, 15, 20 years and more. All right. And by the way, if you are new to the Eclipse open source ecosystem in IoT and Edge and you want an easy introduction to it, well, there is this book that I wrote in order for people to be able to navigate it easier. So, well, have a look if you are new to this and you want an easy introduction to the various building blocks that are available. So thank you so much for listening today. As a reminder, I'm Frédéric Desbiens, Program Manager for IoT and Edge Computing at the Eclipse Foundation. And you can find me as Blueberry Coder on Twitter. For how long, I'm not sure. And on LinkedIn as well. So don't hesitate to connect. So thank you.
Amazing. Thank you so, so much again, Frédéric, for the presentation. If anybody has any questions, please feel free to drop them in the Ask a Questions tab or even in the chat. And we'll just take a few moments to do that. But I'll take an opportunity to let everybody know that we do have the 2023 IoT and Edge Developer and Adoption Survey. It is now open. So if you do click on the little shiny green bar at the bottom of the screen that you could see, it will direct you. To the survey, and you'll be able to complete that. We do have our next presenter, Matthias and Kai, that will be on with us in just a couple of moments. So at 11 o'clock.
And one thing worth mentioning about the survey, this is not us, let's say, taking data from IoT and Edge developers and then keeping that for us or keeping that for our members. All of those survey reports after the surveys happen are published under a Creative Commons license, which means that you can integrate those slides in your own decks by giving attribution to the Eclipse Foundation. You can remix them, you can modify them, and still present the data. So as long as you say that it comes from Eclipse, it's fine. So this is our way to survey current trends in the industry and make sure that our open source contributors and committers are aware of them in order to build better open source projects. But really, anyone can use this. So when I say we are about transparency and openness at the Eclipse Foundation, this is true. Everything that we do is public. Everything that we do is transparent. And we give back all the time to the community as well.
100%. Yes, I echo that. Well, it doesn't look like we have any questions. So thank you again, Frédéric, and we're going to close this session out and be back with you in just a couple of minutes.
Thank you very much. Have a fantastic rest of the day.
Welcome back, everyone. Joining us now is Kai for their talk on enabling Eclipse Hono on Google Cloud as a replacement for Google's Cloud IoT Core. Kai, over to you.
Wait a second. We need to wait for the main
Matthias.
Sorry?
We're waiting for Matthias.
Yeah, exactly. So maybe he has some trouble joining or connecting. I don't know.
Yes, we sent him a couple of I am here.
Oh, he's here. Okay.
Yeah. Matthias, he just keeps on rejecting the invitation. Matthias, can you accept the invitation? While we wait, how's your golf season going, Kai?
Matthias Kemmer.
Oh.
So you will need to send the invitation to Matthias Feuerl.
Yes.
There are two Matthiases at Sotec. So.
Okay, let's resend this here. Golf is going well then. That's good. Where do you go golfing?
I visited a friend in northern Italy, in Bergamo, close to Milan, and was, of course, better weather than in Germany, so that was a nice experience. There we are.
Amazing.
Oh,
hi, Matthias.
Finally.
I kept on clicking for Matthias to click, and he kept on rejecting, and there you are. Well, welcome. So I will pass this over to you two. Feel free to screen share whenever you're ready, and thank you so much, everyone, for your patience.
At least I cannot hear you anymore, Matthias, but maybe that is by intention.
No, I can't hear him either, but I will. You just have to click on unmute, Matthias, if you can, please.
Technical issues. No, at least I can't hear you.
No, we can't hear you. That's okay. You maybe just reset and then we'll come back in. Yeah, that's no problem.
Can you hear me now?
Absolutely.
Okay. What is this? This is a great start. Okay.
It's going to get really good soon.
Okay, so let's get started. So you just heard from Frederic in his keynote a couple of minutes ago that Google will shut down its managed IoT platform, Cloud IoT Core. And our talk will exactly be about how we enabled Eclipse Hono. We're part of the Eclipse IoT tools as a replacement for this platform. So let me first introduce ourselves. My name is Matthias Feurer. I'm working at Sotec, a company in the southwest of Germany, and I'm leading a team of engineers, hardware engineers, embedded software and cloud engineers. I work in the IoT area for nearly 2 decades now. So I've been working for paper automation in 2004. And we have been handling basically the same things that we do now, which was not called IoT at that time. And yeah, switched to Sotec in 2009 and basically did IoT things all over. Then I will switch to Kai.
Yeah, my name is Kai. I work for Bosch. I've been around Eclipse IoT for quite some time now. So I'm not sure if I need further introduction, but for those of you who don't know me, I work for Bosch. I have been working on cloud-based IoT solutions, and in particular, I have started the Eclipse Hono project, and I'm the project lead of that project as well. And I helped Matthias and the Sotec team in doing what they did and what he will tell you about now.
Okay, thank you. Then just a few words about Sotec, the company I'm working for. So as said, we are in the southwest of Germany. We are developing software and hardware solutions. We are a 16 people company here, so we have a quite broad range of things we do. We mainly develop for Google Cloud. We are a Google Cloud partner since 2009. Got this Partner of the Year in IoT Award 2019. And what we do is building digital platforms from hardware over software to cloud and also machine learning. Then just as an agenda, what we will talk about today, we will give you an overview of what Cloud IoT Core is, also the specifics of Cloud IoT Core. Then mainly Kai will give us an overview over Eclipse Hono. Then we will present the contributions we have made and we are currently still making to Eclipse Hono. And we will finish with a live demo of the system. Okay, so Cloud IoT Core is a managed platform from Google, launched in May 2017 as private beta, then general available since 2018. And last year, Google has announced that it will be shut down in August this year. It's fully managed by Google. So what they provide is the global ingest endpoint to Google Cloud Platform with using the Google Worldwide Network, so a low latency worldwide. It has a complete volume-based pricing, so you will be billed per data transferred to the cloud and from the cloud. It provides an MQTT and HTTP protocol endpoint, and it's highly integrated into GCP, of course, meaning all messages transferred to it are forwarded to Cloud PubSub, managed messaging infrastructure from Google. And of course, it's also embedded into the Cloud Console with logging, monitoring, etc. Then this picture shows an IoT reference architecture from Google, where you have on the very left side constrained devices that have they cannot communicate via TCP protocols, so they communicate via Bluetooth or Zigbee or whatever. And then you have the standard gateway devices which can connect to the cloud via TCP protocols. And this is for Google IoT Core HTTP and MQTT. And here in the middle of the diagram, we have the Cloud IoT Core, a central ingest point for those devices. So Google wanted them to all connect to this central place, and from there the data is forwarded to Cloud PubSub and then to the various cloud services where data is stored, transformed, visualized, etc. So then in this picture, we see the main components of Cloud IoT Core without really knowing the implementation details, as this has not been made public. But what we know is that there is a device manager, and this is responsible for registering and configuring devices, which can be done via REST API and also UI. It also allows configuring credentials for a device with a public key or certificate, and this is then used for a JWT-based authentication. And then the device manager also provides features of what I call a mini digital twin. So it stores states sent by a device to the cloud, and it also is able to store configuration data that can be sent from the cloud to a device. Then we have a protocol bridge for MQTT and HTTP, and this allows telemetry and state data sent from device to cloud, and then configuration and command data from cloud to device, where command data is like a fire and forget. So if the device is not connected, it will not transmit it to the device. Configuration data, however, is, as I said, stored inside the device manager and is sent to the device each time it connects. And then the third component is a data broker that is forwarding all the telemetry data to Cloud PubSub. Yeah, so I think Frédéric talked about this also in his keynote, and I have some personal opinions on this as well. So we see that there is a growing IoT graveyard. So not only Google, but also others have killed their managed IoT platforms or are just killing them. And what I can see is that the business models in IoT are still challenging, and this applies for both for the IoT device and end user operators, but also for the providers of managed IoT platforms. And when I, as a IoT device operator, commit to a managed platform, I think I need trust. I need trust that the pricing model will not change in a way that it kills my business model. And I need trust that the platform still exists in a few years, which is obviously an issue nowadays. And I need also the trust that the provider is innovating and updating the platform with new features over time. And then all the providers have the dilemma that they need to provide a platform that fits all different usage patterns in volume and update rate of the ones which are operating the IoT devices. And we have seen various customers whose use cases just didn't fit into this one size. So they selected different strategies for connecting their IoT devices. So when we compare now open source versus managed platforms, I think we can see pros and cons on both sides. Open source has the advantage of customizability, versus on managed platforms, you have the sink or swim approach. On open source, you have a vendor flexibility, so you can take the stack usually and operate it on a different vendor, whereas the managed platforms, you are locked in and with all the negatives and positive sides. And on open source, you have of course, you have the burden of the DevOps costs, while on managed platforms, you don't have to care about the DevOps. So when Google decided to shut down IoT Core, we as a Google partner, Google Cloud partner, and with customers in this area, were asked by Google, but also had to think about with our own products what could be an alternative for IoT Core. And we also had a look into the community forums and studied the reactions there. So, for example, classic Google, hopefully they will open source whatever they worked on. Yeah, they unfortunately didn't. Or killed by Google says it all. Today it's Google Cloud IoT Core. Tomorrow it could be another giant cloud IoT service provider. Use open source or face the consequences. So we thought, okay, maybe open source would be an approach, and it's not the worst. And that's where we came across Eclipse Hono, and I will hand over to Kai for presenting Hono.
Thank you, Matthias. So Eclipse Hono, for those of you who don't know already, it provides a uniform API that you can use in your backend or cloud-based applications to interact with connected devices. And we're talking about millions of devices, and these devices can be connected using arbitrary communication protocols. The picture on the left-hand side is supposed to illustrate the overall concept. At the bottom, you see the connected things or devices. They can use a set of protocols that come out of the box, which are HTTP, MQTT, CoAP, and AMQP 1.0. But you can also roll your own and provide a custom so-called protocol adapter if you have a homegrown protocol that you want to use. Then a little blurred out on the left-hand side, you see this arrow facing up called telemetry. That means the data coming from things that can be consumed by your northbound applications, the solutions. And they can be consumed using a standard API, which originally had been AMQP 1.0 based, but in the meantime has been replaced by Kafka, which you will see in one of the next slides. Then the other direction from the backend to the devices is what we call command and control, meaning you can also use this uniform API to send commands to any of the connected things down below. And these commands can be one-way, meaning kind of fire and forget, or they can be request response, where you actually also expect a response coming back from the device. So next slide, please, Matthias. So the overall architecture has been designed to account for the fact that in standard or in most IoT applications, the volume of the telemetry data flowing from the things to the cloud is much larger than the number of commands being sent down to them. And we're talking about orders of magnitude. So the telemetry direction is generally optimized for throughput and scales out with the number of messages. And we have been conducting tests with I think 1.5 million connected MQTT devices, which send hundreds of thousands of messages per second using the MQTT protocol. So this scales out horizontally. We have also done some scale out tests there. And the other direction, the command and control, is usually optimized for reliability, meaning you want to make sure that a command actually reaches a thing or a device, and it scales out with the number of devices usually. So the things, as pointed out, can use existing protocols, and on the cloud side, you can deploy Hono to, or most easy deployment is if you want to deploy to a Kubernetes cluster. And luckily, you have lots of options of having at least a managed Kubernetes cluster these days on any cloud provider platform. So it's usually not very hard to get Hono up and running. There's also a Helm chart being developed for Hono, which you can use to literally start up a cluster in a matter of minutes. So all the components of Hono are provided as Docker containers. We release them every several months. We do a minor version upgrade, and this is also how the SOTEC guys fit into the process. So the contributions that Matthias will be talking about will find their way into the next minor release updates, I think, during the next 1 or 2 months, I think. Next slide. So this is the architecture overview, the components that a typical Hono deployment consists of. The Hono instance components are the orange ones. So you see immediately that it has great resemblance with the picture that Matthias showed for the Google IoT Core. On the left-hand side, you have the HTTP adapter, the MQTT adapter, AMQP adapter, and you could also have the CoAP adapter and your custom adapter. So those bridge between the transport protocols that are used by the devices and the internal communication protocol. So on the right-hand side, you see this dotted box, the Kafka cluster, which is what we call the messaging infrastructure, which is mainly used to interact with the downstream applications. So on the right-hand side in the solution tier, you see these applications. They connect to the Kafka broker to receive telemetry data produced by the devices on the left-hand side, or they use the Kafka broker to send commands, which are then routed by the command router component to the protocol adapters that the devices are connected to, and from there back to the devices. We also have monitoring infrastructure support, so all of the components expose scraping endpoints for Prometheus, which you can then use to gather information, which can then be displayed in a Grafana dashboard. One thing to note, the communication paths, the internal paths between the components that are depicted in orange and entitled AMQP 1.0, those are peer-to-peer communication routes, meaning these components speak using AMQP 1.0 with each other, but they do not require any message broker or something. It's direct peer-to-peer communication. So this mainly stems from the original times when we used an AMQP 1.0 based messaging infrastructure on the right as well. But there have been some plans of maybe replacing this with gRPC-based communication, but this is an open issue. Okay, I think that's all I wanted to say. That's all I wanted to say. Now it's back to you, Matthias.
Yeah, thank you for introducing Hono. So we, of course, looked also at other open source solutions besides Hono, but what finally convinced us of Hono is the following pros we found. So it's an actively used product. So with Bosch using it, but also KiwiGrid, which is also a customer of us, and a Loxy. So we were convinced that, yeah, it's not only a theoretical thing, but it's really being used in production. It's a living project and community, which is really important, which you can see on the right hand side in the commit graph. And what was also important for us, it has a clean and structured code base. So you could see that somebody is really having an eye on that the code is consistent. And other advantages were that it's a Kubernetes-based deployment, as Kai just mentioned. And the programming language is also something that is important because you need to have the resources which are capable of developing the code. So yeah, that's why we finally decided for using Hono and enabling it as a replacement, which leads me to the contributions we did and we are still doing to the Hono project. So the question was, how can we make Hono behave like IoT Core? And there were basically two challenges with that. First one, and this is the major one, is that we wanted to have minimal changes to the firmware or software of existing devices which are connected to IoT Core, because this is something that is it's a high burden for the ones operating those devices. So we tried to make this as similar as possible, and on the other hand, we wanted to have a seamless integration of Hono into Google Cloud and to existing business applications, which means that it's this is not so hard as the device upgrades, but there are existing cloud applications which rely on the messages coming from PubSub. So ideally, this should work the same after we did our work. Yeah.
Okay, so but a wolf obviously is not a sheep, and when Matthias and his team approached me initially and we talked about what they wanted to do, there were of course some trade-offs to be made, or some things that were important to me that were obviously, of course, not so important to Matthias and his team from the beginning. And some of those are, for example, and as Matthias already pointed out, we take great care of providing a well-established and stable API. So the uniform APIs that we have, they are not really specific to any particular cloud environment or whatever. So, however, what Matthias and his team wanted to do was try to tie in devices that were used to connect to Google IoT Core with minimal changes, meaning they would need some features that are potentially not there yet in these APIs. And on the other hand, they would not care about implementing all of the other stuff that the Hono APIs actually provide and guarantee to consumers. So we needed to talk a little about expectations and how we want to trade one off against the other. So that was one thing. Then, of course, we do have some very strong core concepts in Hono, in particular from an architectural point of view. And we do not, or at least I do not tend to easily sacrifice those, as Matthias and his team have already seen in various discussions that we had already. But on the other hand, of course, we need to find ways in order to to let this IoT core specific functionality find their way into it. And I think on a case-by-case basis, we were very successful in actually doing that. Then there is a general question of what is actually in scope of Hono and what is out of scope. So, for example, the smaller or the low-cost digital twin that Matthias was talking about with the device configuration, that is something that Hono's device registry is simply not designed to contain and should not contain. So it was a decision to be made how we could get this into the picture, and finally we ended up with having the device configuration in a backend application, meaning that would be application land from Hono's point of view versus this is part of Hono's functionality. And with all of this, it was always important to try to find a balance between following the principles that we have with Hono versus making sure that Matthias and his team are able to actually get things up and running in an overseeable amount of time. So we are currently pretty much at the final part of the journey, I would say. Matthias, would you agree? And
Yep.
So far, I think we managed to get things done pretty well.
I agree, yeah. So what were the features missing in Hono from our perspective? So this was the authentication mechanism used by IoT Core, which is based on a JWT-based private public key authentication system. Then the integration into PubSub, Cloud SQL integration, that was not so hard. Cloud SQL is a managed PostgreSQL database. Then the state and config mini digital twin thing that we just talked about. Then IoT Core has a REST API for communicating with the devices, sending down configs and commands. Then Hono did not have a web UI front end, but IoT Core was embedded into the GCP console. And finally, we wanted to have an automatic deployment which sets up all the GCP resources and installs the Hono software. Yeah, so that's basically what I will talk about now. So first, the authentication, which was, let's say, a smaller part of what we contributed. So we added a new credential type raw public key for the JWT-based authentication. So the MQTT adapter is now supporting JWT credentials by accepting JSON Web Token in the password field, assigned JSON Web Token in the password field, and the signature is then checked against the raw public key, which is stored in the database. The username in this case is ignored, so that's exactly the mimic from IoT Core. Then the bigger thing was enabling PubSub as a messaging infrastructure. And to just show again what this means, the messaging infrastructure is not part of Hono itself. Instead, Hono can use different kinds of messaging infrastructure, as Kai also explained. So I think in the default case, this is Kafka. In former times, it could have been also AMQP, or maybe can still be AMQP. And we now enabled another messaging structure, namely PubSub. And the messaging infrastructure is used for sending telemetry data down to business applications, but also for receiving command and control and sending those to the appropriate MQTT adapter instances and then down to, up to the devices. Yeah, so we enabled this for internal and external messaging. So with internal, I mean that also the internal components are communicating via PubSub. So we completely removed the Kafka from the system. So this is all replaced by PubSub. It's configured via a project ID, and authentication in Google Kubernetes Engine is with a workload identity. The topics are created automatically, but in an extra component that I will talk about later. So you won't have to create the topics yourself. And then we have a special handling of subfolders, which is also due to the fact that IoT Core was doing it like that. So MQTT subfolders are mapped to subtopics in PubSub. And below we see a sequence diagram of a device sending event data with quality of service level 1 to the MQTT adapter, which is then translated to a specific topic on PubSub. And only when PubSub acknowledges the message, the MQTT adapter will send an acknowledgement back to the device. Yeah, then the device communication API. So this is an API that is basically doing the same thing as the IoT Core API was doing before or is doing right now. So it's used for sending commands to the device and configs, and you can also list configs. And this is now not in the Hono Core project. It's contributed to the Hono Extras project, but is in our installation. Yeah, is installed alongside with Hono. Yeah, and then we developed an Angular-based web front end for management of tenants, devices, and credentials. You can also use the communication out from the UI for sending configuration and commands. And you can also see this mini digital twin information inside the UI, and the front end was also contributed to the Hono's Extra repository. Yeah, and finally, we developed a Terraform deployment script, which has two parts. One is setting up all infrastructure on Google Cloud, including Kubernetes Engine, Cloud SQL, load balancers, etc. And the second part is then deploying Hono itself using the Helm charts and including all components I just talked about from the Hono Extras repositories. And this leads us to an architecture that looks like this on Google Cloud Platform. So on the left hand, we have again the edge device with an MQTT client that can connect to the MQTT adapter. Here in orange, we have components that existed before in Hono but were adjusted. So this is the MQTT adapter now with a PubSub bridge, the device registry, and the command router. So this is basically a Hono running on GCP. And then we have one block with the messaging infrastructure, which is now Google Cloud PubSub. And on the right-hand side, we have custom IoT solutions that should basically look and operate the same as before. And in the middle and in the bottom, we have new components that were developed by us and contributed to the Hono Extras repository, which is the UI and the communication API. And then we have secured the whole system with identity-aware proxy and cloud endpoints. These are two Google services, for authentication and for API management. So, and I think this leads us to the demo. Let me see. I think I have to share now something else. Let me see. So I will first show you a setup on Google Cloud. Let me zoom in a bit. So this is a deployment of Hono in a Google Cloud project on our sandbox project that we use for testing. And we see here, we have here the MQTT adapter, the Hono components that come also with the, let's say, the traditional Hono. And then we have this new communication API deployed and also a device management UI. And then here another pod which is not included in the default Hono, which is doing the API management via cloud endpoints. Then let me switch over quickly to Cloud PubSub console. So this is showing for a telemetry topic in Cloud PubSub the messages we have received. So I did some load tests before, so you can see here some messages, and we will just see a message in a second sent from an active MQTT client. And then maybe the most interesting. So this one shows the UI we have developed. It starts with a list of tenants, with Hono tenants. So you can list the tenants, you can create new tenants and select one of the supported messaging types, tenant-based. So you could support multiple messaging infrastructures on the same deployment if you want. And then let's go into a tenant, and then you get a list of devices that are in the device registry from Hono. You can create new devices, and for a device, you then have some information about the used authentication type. So this is now the new JWT-based authentication. We have provided a public key in here. Yeah, could also be a certificate, and you can see some configuration data that we have sent to the device before. So this is base 64 encoded data and some state information that this test device has sent to the cloud. So this is what I call the mini digital twin. So state information from the device and configuration data sent down to the device. Okay, I think I would like to share some external application now using, let me just see if I can do this. Yeah, that's possible. Okay. Can you see my screen?
Yeah.
I think yes. Okay, so now I'm connecting with an MQTT client to our Hono sandbox. And as said, I provide a JWT in the password field. Username is unused. And what now happens is that on Hono side, we get the latest config for this device and send it down. So this is the latest configuration that was provided on the cloud and is immediately sent down to the device. And we will send a message up to the cloud, and we'll see on PubSub if this message is processed by Hono and then forwarded. So I just try to pull the message, and here it is. And then we will send a configuration down to the device. This is received here. And I will also send a command. And I can also give a command subfolder, so I can specify some subfolders on MQTT where the command will be sent to. And when I go to the MQTT client, this should be received here. Yeah. So yeah, that's basically it, I think, and I have shown everything I wanted. So I think we can open the questions and answers.
So there was one question in the chat that I've seen already from Stephen. He was asking why or what the reasons were to switch from AMQP 1.0 to Kafka, I guess, for the messaging infrastructure. So originally we used AMQP 1.0 all over the system, in between the components and as the messaging infrastructure to connect to the applications. The protocol itself is great. In particular, it supports something called back pressure, which means that you can actually prevent senders from sending messages that are unwanted by receivers or not processable. So you can implement some nice way of flow control across components. But when it comes to implementations of AMQP 1.0, we found it very difficult to find a stable setup. There used to be a project called En Masse, which was mainly driven by Red Hat, which provided an AMQP 1.0 based messaging infrastructure, which was able to scale out to a certain number of nodes. This worked quite well as long as we did not put too much volume on it, but then it became less and less stable, or we ran into problems that needed to be fixed over and over. And so in the end, it seemed much easier to actually use something like Apache Kafka, which was by then already very much established in this whole area or this field of messaging. And so we decided to give that a shot and try to integrate it for the downstream direction. And once that was working very well for telemetry and events, we also were able to use it for the command and control direction. And since this has a very, very large community and is already very, very stable, we decided to use that as the default implementation for the messaging infrastructure. And another point is you can easily get managed Kafka as well on most major cloud platforms. So you do not have to operate that yourself.
Amazing. And so I just wanted to take this opportunity to thank you both for the excellent presentation and just encourage anybody for any other questions that they may have to put them in the Ask a Questions tab or in the chat. I did see, Kai, that you were responding as we were going through the presentation. Thank you for that. So is there any other last minute questions at all? No. Okay. All right. Well, thank you so much. This concludes your talk, and we will be back on at 12:15 for our next presentation. Thank you, everyone.
Thank you.
Thank you.
Thank you.
Bye. Welcome, Sinsin, to Virtual IoT and Edge Days, and welcome back, everybody. Today, Sinsin will be having a talk from now until about 1 o'clock this afternoon, Eastern Standard Time. So, Sinsin, I'll pass this over to you.
Yeah, thanks. Thank you.
Thank you.
My screen. All right. Yeah, let's get started. Today, I'm going to talk about building an IoT device SDK from a Web3 perspective. I'm Xinxin Fan, head for cryptography at IoTex. Okay. Here's today's outline. Firstly, I would like to explain why we start considering building the embedded SDK, especially for Web3 type of applications. In the second part, I will basically briefly touch upon some key concepts about self-sovereign identities. I think that's one of the key building blocks when you're considering the Web3 type of application. So third part, I will talk about Web3 IoT embedded SDK. That's actually the initiative done by the IoTex. Currently, this project is ongoing, and we highly encourage other open source developers can join this project to revolve the Web3 together with us. Okay. Without further ado, let's get started. Firstly, why we starting looking at the embedded SDK from the Web3 perspective, right? So this is a very first question. I think the people in the Eclipse community or embedded community would like to ask. Yeah, we all know the traditional IoT system are largely centralized, right? So you either can build your application, deploy all the application in the cloud environments, or you can rely on some edge-centric systems to deploy your applications. Either way is largely centralized, right? So you deploy your application using either cloud setting or the edge setting, then you transfer the value to your customers. The business model actually in a centralized IoT application is quite straightforward, right? So you're starting your value chain from like a device manufacturer until it's reached to the end customers. As already been mentioned by the previous speakers, the traditional IoT system, or Web2-based IoT system, already facing a lot of challenges, especially from the business model perspective. So is IoT died? Definitely not, right? So in here, we are aware the value generated by the IoT device and systems, how they can change the business decision, also to create additional values to the users. The way we actually need to think about is to find a more effective way or new business models to revive the IoT business. Since the occurrence of blockchain and Web3, we already see there's enormous amount of applications building on top of blockchain and Web3. People from the different industry sectors starting exploring how blockchain and Web3 can transform their own business. So there's actually a very nice set of features provided by the blockchain, like I listed here: decentralization, consensus, immutability, security, privacy, smart contracts, etc. So for different industry sectors, they may use a subset or all of those features to transform their own business. Yeah, starting from the 2020, actually, we already see a few wave of large category of blockchain applications. They try to deal with financial assets, starting like from 2020, what we called the year of DeFi, right? So at that time, the community or developers using the data available on the blockchain to build all kinds of decentralized finance applications, try to change the way people interact with the financial system. So the reason actually is quite makes sense. At that time, the only the majority of data on the blockchain are the transaction data. So that's the only large set of data you can use for building your applications. So that's why the DeFi becomes the first large category of applications in the blockchain world. In 2021, actually, we call it the year of NFT, right? So once people say, okay, I can really control my asset on the blockchain, how about other type of asset? So that's why NFT came into people's mind, right? So NFT actually represent, you can think it represent something in the real world. Once you tokenize it, you can actually control it or transfer it to other people or trade it, right? So yeah, that's why the 2021 we see a lot of applications surrounding around the NFT. So since 2022, the community is starting thinking about what's other type of data we can use to build financial systems, right? So actually, this come out the concept of machine-fi or machine economy in the more traditional word. So the idea here is that we are aware the IoT creates a huge amount of value for business, especially the IoT device, the data generated from the IoT device or the IoT device themselves. Right? So how about we can find a way to monetize the data generated from the machine, or directly monetize the utility of the machine to create the new businesses. So in this way, actually, we can incentivize the entire community to build the IoT infrastructure to address both challenges in the enterprise domain as well as the consumer domains. Yeah, this come out the concept of what's called the machine economy, right? So this machine economy actually is a network smart, connected, and economically independent devices and machines. They act as autonomous market participants. Essentially, we are going to utilize the data generated from the machine or the utility of the machine itself to create large-scale decentralized network. There are three key enablers to make it happen. The first one definitely is Internet of Things. Actually, just serve all the IoT devices. Actually, they serve as agents. They can provide the real-time information about what's happening in the real world and give you an opportunity to tokenize the data or utility of the IoT device or the IoT device, so that you can generate a tokenized marketplace. Second pillar, also extremely important, distributed ledger technology. That one actually they provide you the platform. You can do the transactions without relying on the trusted intermediaries. Most importantly, the distributed ledger or blockchain, they bring an element of finite supply so that you can create a so-called internet of value. Once you tokenize the data generated from the IoT device or the utility of the device itself, you can create the internet of value. Third pillar is the tokenomics. Actually, you need some kind of mechanism to address the cold start problem that's actually facing by many IoT device manufacturers and other ecosystem stakeholders. Most importantly, you need to find a way to encourage or incentivize the community to build large-scale infrastructure to address the long-term sustainability issues. So yeah, these are basically three key pillars if you want to build a successful machine economy. Why we are doing that, right? So like I mentioned before, traditional IoT business models actually facing a lot of challenges. That's why we already witness a lot of IoT cloud service providers has shut down their business. Yeah, the occurrence of blockchain and Web3 actually shed a light to IoT industry. Basically, you can explore the new business models. Like I show in this figure, actually there's a multiple way you can explore the new business models. For example, if you are a device manufacturer, instead of you try to get a large amount of funding initially to create your IoT device, actually you can create a DAO, to basically incentivize the community members or institution investors to join this process at the very beginning. By forming a DAO and distribute the reward to your community members or institutional investors, you can relatively easy to address the cold start problem. If you do not have a large amount of funding initially, you can through this way to bootstrap your project. As a solution providers, actually you can say, okay, I will build a large scale decentralized application. This is my token models. How I incentivize my community to help me to build this entire network all together. And this is a way we can distribute the reward to incentivize the large community members to deploy the certain type of IoT device. All those rules or all those rules can be defined using smart contract, which will be sit on top of the blockchain. So in this way, it can be trusted by the entire community members. Here, just list a few ways you can think about your IoT go-to-market strategy and the customer engagement approach. So this new type of business models basically made IoT business interesting again. That's why we consider how we can build this all together. A traditional embedded SDK provided by the cloud service provider like AWS works in this way. You usually download that SDK, installed into your device, then they can interact with IoT core in the AWS. Then further you can build your IoT applications. So this IoT device SDK provided by the cloud service provider enable your device to communicate with a particular cloud. So in this, once your SDK has been installed, actually the way to build your IoT application is that you create some kind of digital twin to represent the device in the physical world. The way the cloud service provider is going to do is that they will allow you to download a set of certificates for all your device. Once those certificates has been installed in the device, then they can securely communicate with the IoT gateway in the cloud environments. Then you can create a device shadow, or you can think it's type of digital twin to interact with other services on behalf of the real device. Yeah, this type of model or embedded SDK can address all of those requirements in the traditional Web 2-based IoT system. They enable your device to interact with other services, and you can further build a traditional Web 2-based IoT applications on top of that. If we consider how we can enable the device to join the Web3 applications, actually we need more. The Web3 emphasize on the control and ownership. But a very important concept in Web3 space is self-sovereign identities. So in the second part of my talk, let's look into what is key concept and how it will affect the design of embedded SDK. Yeah, overall speaking, actually we for using the SSI or self-sovereign identity technology, we still need to deal with 3 key pillars. Yeah, the first one is called decentralized identifier. Actually, it's a new type of identifier you can use to represent actually everything: people, device, organization, any other entities. Yeah, second one is called verifiable credential. That's one basically will bring the trust among the different entities in your system. Yeah, the third pillar is called DID-COM messaging. Basically, this DID-COM messaging will define how two entities which are identified by the decentralized identifier can communicate with each other. Yeah, once you have these three pillars, actually you can form the arbitrary relationship among the different entities. Remember, in the traditional centralized or Web 2 based IoT applications, you mostly rely on the certificates to bring the trust. In the SSI case, actually the DID, they will be anchored onto the blockchain, and you can read or write the DID, and by exchanging the verifiable credential, one or multiple verifiable credential, you can establish a trust with other entities. Yeah, I believe people are already familiar with X509 certificates if you have been dealing with IoT. SSI actually deal with try to address the same identity issues from the different angle, right? Like I showed in this figure, to really build identity, you need an identifier, you need a public key, also the identity attributes. Right? So for X509 case, like you can see in the red corner, everything will be encapsulated into a X5509 certificate, right? In the main body, you capture the identifier, public key, and you can use the extension field to add the attestation for additional attributes. This certificate will be signed by a CA, right? So there is a certificate chain or hierarchical architecture. Basically, you need to trust the CA in order to establish the trust among the different entities. SSI, on the other hand, they have a separation between identifier and identity attributes, right? So in this way, they provide very flexible way. You can basically enable different like verifiable credential issuer to attest the different attributes. Yeah, let's have a brief look at what's the DID, right? DID is just another type of a globally unique identifier, like it's shown in this way. They have like three components. First one is a schema. It's just DID that's fixed for all type of DIDs. The second one is called second component called the DID method, right? So this DID method will specify how a decentralized identifier can be created, read, updated, deleted, basically implementing the CRUD operations. The third one, third component is the DID method specific strings. Yeah, actually, this one is the context specific and should be unique within the context of the DID method. There are four core properties about a decentralized identifier. Firstly, also very important, is a decentralized identifier, which means there's no centralized registration authorities required. You can generate it yourself, generate it within a device, etc. Right. Second, very important property is this identifier is cryptographically verifiable identifier, which means you can prove to the other party actually you are control this ID. It's unlike the many traditional identifier like the email address, etc., which is actually controlled by the third party. The DID's control can be by yourself or by your device. Yeah, third one is a permanent, persistent identifier. You never need to change. Also, it's a resolvable identifier. It can be further look up to see what's behind this string. Another very important concept called DID documents, right? So the DID identifier itself does not provide you too much information. It's just of a numerical string, like I show it here. But once you use a DID resolver, you can find more information behind this identifier. The DID document provides a lot of informations. For example, to interact with this identity behind this identifier, what is the service endpoint you need to talk to, and which key you need to use for authentication and encryption. So essentially, DID document give you more information how you should or how you can interact with another entity in a secure manner. Yeah, this is like the JSON IOD representation of a DID document. You can see we have the ID here. We also have the public key which associate with this DID. Also, we have the authentication method and corresponding public key, which means if you want to authenticate a message you send from me, you can use this particular authentication method. The service endpoint lists the several one or multiple endpoint you can interact with me, for example, through the HTTP channel, MQTT channel, etc. The last part is a proof. Actually, I can sign this document to show this document is under my control. Very short summary about the decentralized identifier. There's a number of key concepts. You can, firstly, you can generate the DID. That one will identify a DID subject, and this DID will be anchored onto a verifiable data registry, which could be a blockchain, a decentralized data store, etc. You can, the DID will be generated using the DID method, and the DID can be resolved using a DID resolver. Once you resolve this DID, you will get back a DID documents, which including more detailed information how you can interact with a DID subject. Yeah. Also, you can define who is the controller for the DID documents. It might be yourself, might be somebody else. Yeah. Second, very important information is about verifiable credentials. Verifiable credentials is, I think people are familiar with this concept. You just open your wallet. It's all kinds of physical credentials, your credit card, social security number, etc. Verifiable credentials actually try to mimic what you have in your wallet. So essentially, they provide a digital version of physical credentials. You carry it in your wallet every day, and allow you to prove to the other entities a set of claim about identifier. So you can receive the verifiable credentials from the actually different entities. It's like you get your bank card from a bank, you get a driver license from DFA, etc. Yeah, exactly try to mimic this concept. For the verifiable credential ecosystem, actually, you or your device may be the credential holder. There's an issuer will issue the credential for the holder. In the particular application, you can have a governance process to determine who will be the issuer. Yeah, once the holder receive the credentials, they will store in identity wallet. Then once they need to interact with the other service, they will present this credential to show I meet your requirements. So all the different participants inside the system, you can retrieve the DID to see who is the issuer, who is the verifier, who will be the identity holders. As we recall from the previous figure, all those information is recorded in the verifiable data registry. Yeah, similar to a DID documents, the verifiable credential also can be represented in a JSON IOD format. It contains some metadata like what's the credential ID and which type of credential it is, and most importantly, a set of claims. This basically will attest the identity attributes about particular ID. Right. For example, if you want to issue a verifiable credential to your device, you can say, okay, my device has a trust zone enabled, have a security storage, have the crypto accelerator, etc. You can all list all those security related features in a set of claims. So in this way, once other people, once other projects want your device, they can verify this claim to see, okay, I can trust this device. Also, they contain a cryptographic proof, which is essentially a digital signature from the credential issuer. Yeah, the third, the last pillar is about DID-COM messaging. Like already mentioned before, DID-COM messaging actually they define a framework for safe structured interaction between two DID identified entities. So from this figure, you can see DID-COM messaging just define the format of the message is independent from the which transportation layer protocol you are going to use. So in this way, once you have the DID identified entities, you can, by exchanging this messaging to complete a different type of protocols. On top of this basic definition of different messaging, you can build other protocols. I here give you like 2 examples. For example, first one, how I can connect to another party. Yeah, the way is that this can be done either explicitly or implicitly. For the explicit way, actually you can use out-of-band approach by scanning a QR code, access the URL, etc. Or implicit way, you can resolve the DID document to get the other party's information. I'll give you a sequence diagram here just to show how this could work. So very important, some important use cases is that if an IoT device has a service endpoint, which is documented in his DID document, actually they can allow other people to connect to this device for reading data. Yeah, the other example is authentication, right? So this authentication message exchange basically allow the 2 entities to mutually authenticate each other by disclosing and verifying their DIDs. Yeah, again, we can send here is a sequence diagram for the mutual authentication between a requester and the responder. Right. So by resolving the DID documents, you can actually verify the message sent from the other party. It's similar to traditional mutual authentication protocol, but described in the DID-COM messaging format. Typical use case, like IoT device, they want to make sure that only valid parties already connect to it before allowing the further access. Okay. Yeah, I think those are very important 3 key pillars for building for using the SSI technology. So this one actually give the control back to the user or the device owner or even device itself, depending on your application scenarios. This part, I think, is key building blocks if you want to participate different type of machine-driven Web3 applications. Yeah, lastly, I want to briefly talk about the Web3 IoT embedded SDK. That is ongoing work in IoTeX. We try to adding the what I already described here to package it into an embedded SDK, which can later be used by various IoT devices. So what is Web3 IoT? Actually, it's an embedded SDK for connecting IoT device, either big one or smaller one, to Web3. You can see we try to cover a large range of IoT device from the smaller one to the like open source hardware board or the other popular tools using by the embedded community. We aim to adding the necessary components to this SDK, and you can use this one to further build your application to join the decentralized world. There are several design goals from our side. Firstly, is openness. Everything is open source. We try to encourage the collaboration in the open source community. Second one is trustworthiness. We follow the industry best practice to build this SDK. Also, third one is modularity. we try to divide into the different modules. Then you itself can be easily maintained and upgraded. Firstly, if you target for the enterprise applications, you may have some opportunity to doing certification. We use like the ARM PSA API to implement the security-related function. You might be able to get that certification. Yeah, from the high level, this is what we are going to build. Essentially, we have this number of layers. Fundamentally, there's a root of trust because Web3 applications, essentially, you need to control the assets or transfer the assets. The security is a very important aspect for Web3 applications. We have this few layers dealing with the security. Starting from the root of trust, we'll support a different type of root of trust. If you have a security element on your board, if you have the security enclave or TPM on your board, that will be supported. On top of that, there's a number of cryptography primitives to handling all the crypto operations. On top of that, there's cryptography services. These few layers will be mainly implemented using the ARM PSA cryptography API. So in this way, the developer have a unified way to handling crypto operations. So PSA API provide a very nice set of API definition. So you don't need to care about the details. Just doing the certain number of settings, then you are done, right? So on top of that, we try to add the identity layer and the credential layer. Essentially, will enable your device to generate the decentralized identifiers, to enable your device to verify the credential received from the other party, etc. So this standards is defined by the W3C. We try to follow that standards. On top of that, we also try to implement the DID-COM messaging that defined by the Decentralized Identity Foundation. So this one, as we mentioned before, DID-COM messaging only define the message format, right? So it's independent of exactly transport layer protocols. Then we need to add support for the different protocols like HTTP, MQTT, etc. So based on this high-level architecture, actually, if you implement that, and then on top of this high-level architecture, you can actually build any decentralized applications. So I will briefly touch upon how we deal with the crypto side of implementation due to limited time. Okay. Actually, one goal we have is that we try to support the easily implemented crypto functions for all kinds of IoT devices. Right. So flexibility or also extensibility are the key factors we considered. So we have a list of few layers. For the cryptography primitives, actually we try to support popular embedded crypto libraries you have been used a lot in your IoT applications like embedded TLS, TimeCrypt, etc. Also, you can bring your own crypto if you have the specialized implementation which does not exist in the current library available. You can also implement yours. On top of that is a PSA layer, right? So we try to provide a unified layer to access a crypto service. So in terms of the cryptography services, the TFM, TFA will be supported. Also, if you want to implement yours, that's also an option. We have the config systems. Actually, depending on the resource available on your device or certain development board, you can use these configure tools to select which library or even which primitives you want to add. Then they can you can have the precise estimation like the memory footprint, etc. Right. So also try to support different compile tools, CMake and others, etc. for different type of board. A complete set of testing is also available. for testing the entire service up to the crypto primitives. Okay. Yeah, here's actually a workflow if you want to have a PSA call. So actually there's 4 layers. The first layer will be the API layer. So this is represented by the PSA crypto.c. And the second layer is like a wrapper layer. Yeah, they will decided whether you will go to a slow pass or you want to use a hardware accelerator. Yeah, this layer also handling the storage of the key in the RAM or flash, depending on the lifetime setting of your keys. Also, there's a port layer will handling the diversified requirements from the different board, like Raspberry Pi, Arduino, STM32, etc. Finally, the call will reach to the backend that has a set of crypto libraries you can use, embedded TLS, TinyCrypt, or there's if you have a secure element or other hardware crypto accelerator, if there's a lib there, you can also use. Like mentioned, API layer, they can provide standard PSA API for users. Also, they will separate which type of operations you want to perform, encryption, decryption, hash function, etc. Also, they will do some parameter validation. You can enable the different features where the macro definition this layer. Wrapper layer, they provide the interface for like key storage depending on the key lifetime definition, and they provide interface to access the secure element. Also, they provide the interface for using the crypto acceleration. We have 2 paths here. If there's a hardware accelerator available on your board, they will go to this faster path. Otherwise, they will go to this software implement path. Okay. Yeah, handling the handle layer. They will further select which specific crypto algorithm you are going to use. Then they also correspond. They will convert a PSA call into the corresponding process sequence. Yeah. Also, this port layer will handle the mapping between the error code in the backend library as well as the PSA layer. Yeah, they also convert data for the port layer. Finally, they will interact with the backend to implement what you have called here. Okay. So, what you can do with this SDK, right? So actually, we enable you to build SDK marketplace. We're expecting all the developer to build up upon this SDK for their particular Web3 applications. Like here, if you only want to use the lower layers, starting from the crypto service, primitives, and root of trust, if you only want to use these 3 layers, actually you can build the hardware wallet SDK to store the cryptocurrency, etc. Also, you can build the blockchain layer 1 embedded client using these 2 SDKs. If identity is not of your concern, you can actually use this lower few layers to build hardware wallet or layer 1 blockchain embedded client. So if you say, okay, I do need the identifiers for all my IoT device in order to interact with other services, then you are going to use all those layers. Like ourselves, IoTex, we already use this stack to build what we call the WebStream device SDK, which will enable the different smart device to interact with a decentralized network built by IoTex. Okay. Also, if you want to build an identity wallet for a device or for other applications, you can also use all those 4 layers. Also, if you are into the Metaverse type of application, you can also build a Metaverse SDKs on top of this. Yeah, for long-term vision, we are expecting this SDK can be used by the different semiconductor company to integrate whatever they have built into their own SDK to unlock their device for the new opportunities in the Web3 space. Also, we are looking for integrating what have been built into the open source, like embedded operating systems, like the Oniro projects. We have a member in this working group. Also, there's many other options we are looking at. Yeah, I do believe this is unique opportunities for embedded community or Eclipse community members to join the revolution with the Web3 and to see how you can eventually build the machine-driven large-scale applications to empower either business case or consumer use cases. Yeah, that's all I would like to share today. Thank you very much.
Thank you so much, Sinsen, for this excellent presentation and just full of information. We do have some questions, or one question so far in the Ask a Questions tab from Frédéric. And it says, how mature is the DID standard? Is it stable or changing? Let's start with maybe part one of that question. Mm-hmm. So how mature is the DID standard?
Yeah, I think the DID standard had finally got approved last year by the W3C. I think it's quite stable for now. There's already many startups or even larger corporations using these standards for building either enterprise use cases or consumer-facing use cases. Yeah.
Okay, so it is stable or changing a lot. It's both.
I think the DID, the entire space, still moving fast because people exploring the different applications to see whether it's a new request. I think they will continue evolving in the future, but it's relatively mature. Yeah, for now.
Okay, awesome. And also, are developers adopting it, or are there strong competing alternatives?
Yeah. So in terms of adoption, you can see there's a lot of startups taking this step to building identity-driven applications in traditional Web2 space or even in the Web3 space. Whether is there are strong competing alternatives? Actually, many people still want to use traditional Web2 based identity approach, but I think that's depending on your business requirements for this. Right? So traditional, there is already a lot of vendors provide the Web2 based identity management, but for the Web3 type of application, I think it's new. Also, there's a new opportunities. You can actually provide decentralized identity as a service to address a particular business challenge. But I think it depends on the case-by-case study, which problem you try to resolve using the DID. DID does provide a nice set of security and privacy features, but whether that can bring the value for your particular business need to be further analyzed.
Okay. Perfect. And Frédéric says, thank you for the presentation, Sinsen. So we all thank you so much. So we are up again at 1:15 for our next presentation with Achim. We'll talk to you all soon. Ciao for now.
Thank you. Bye.
Hi.
Hello and welcome back. We today have Akim that will be presenting on his talk at DTLS-CID meets Saphir. Akim, over to you.
Thank you. So welcome all to the session DTLS-CID meets Saphir. Sometimes it's said that using open source comes with the pain of integrating it. And the intention of this session is to show it's also worth doing it. Okay, so my name is Achim Kraus. I have 25 years experience in software development and testing, mainly Java, mainly C. 15 years experience in experience with distributed systems, which already contained devices, some stuff over Internet Protocol, some stuff over ARIS 485. This is a serial protocol, very common in the building industry. And ArcNet, it's a very old protocol, but we really have also this one in the building stuff. And I have 7 years experience with IoT, mainly co-op DTLS and lightweight M2M. I'm a committer in 2 Eclipse projects, Californium and Tiny DTLS. I'm also a committer in Wakama, but this is I'm not longer active there. I'm recently was added as co-author to an RFC, the 9146. This is DTLS 1.2 connection ID. So what is DTLS 1.2 SID? It enables your device to use encryption in a common and constrained network environment with less overhead. Usually you have a lot of overhead if you want to use encryption, and this one reduces this dramatically. It stands for Datagram Transport Layer Security 1.2. This is defined in RFC 6347. And for connection ID, this is this RFC 9146. This session doesn't cover the details of this technique. I focus more on the usage and benefits. So I think with the introduction of rhetoric at the beginning of this day is a little wrong. I hope it's not technical. I hope it shows how to use it. So what I want to present is an integrated playground. So a lot of open source projects playing together and ready to use. So what we see is that we can have a device. So data comes from a device which uses Saphir and Tiny DTLS. It sends the data over a co-op S3 proxy server, which is based on Linux, Californium, and the AWS SDK. And it sends the data into a S3 cloud storage. It visualizes data directly using from S3. And you can then choose a JavaScript browser app in order to visualize this. This session is rather an introduction to the project websites than a tutorial. So my initial idea was really to show these websites, but I withdrawn this idea because I think with the presentation technique, this doesn't work. But you're invited, and if you're curious, please visit afterwards. There's this great project websites. So the intention of this session is also to make a little marketing for all those open source projects which I have integrated here. Even if in the end you mainly need the client project, check it out, and then you need S3, which is not open source, which is a service, and then you're already done. But maybe you are more curious, and then you can have a look on all the other projects. So let's start. If you want to get an overview of this integrated playground, then please open this website of my Saphir Co-op S client. It is just a GitHub repository. It comes with an overview, with a list of recommended tools, means which debugger or which jailing do you need, or whatever you need in order to work with that stuff. A list of supported devices with links so that you know where you can use this software. without efforts or with a little effort, and links how to install the toolchain, so it gets pretty fast. We have pre-compiled firmware images, and I did also add some research about the power consumption, because this is always the question about these cellular devices, how much power they consume, and there is a configuration about documentation. So CFire CoAP S client, this CoAP S, this stands for Constrained Application Protocol in the secure mode. This is pretty much the same as HTTP and HTTPS, so S is for secure. It's a pretty simple CoAP client. It doesn't use too much special stuff, and it's provided by the Zephyr project. We also use just the sensor drivers provided by the Zephyr project. So there is a nice YouTube video from Benjamin where he shows how you add or how you use those drivers for sensors with Zephyr. It's really pretty easy, so watch this. And then we send just a text message to the cloud. I didn't spend time into use JSON or CBOR, basically because the main target group is people which are not that deep into IT, which are more on the device side, and for them it's easier to start with text, and then you can change this later. It uses DTLS 1.2 connection ID for encryption. That's important if you use cellular devices in order to reduce this encryption overhead. One special thing of this client is that it binds some modem and radio events to the DTLS and the CoAP layer. This is pretty easy. So one example is sometimes the modem is off, and then it must go first ready to send. And then if you ready to send, then you start your transmission time. Otherwise, this would not match. So if it takes longer that the modem gets ready to send and your CoAP transmission timer runs, then this doesn't make sense. So this means with binding those modem and radio events to these layers, that really improves the support for power-saving functions like PSM and RAI. And also with that, you can have an advanced network outage detection. One problem of cellular modems is really the network outage, and you detect this and you recover from that. And altogether, you get a really efficient and reliable solution. So just as impression, so a text message is on the left side what I send. It's just a collection of information. So it starts with the uptime. So this device, when I made this screenshot, was 5 days up. It was sending about 140 messages, no retransmissions and no failures. Usually you have retransmissions and usually you have failures. So this is really a lucky shot. Usually you have retransmission. That's no problem. So, and then we have here the battery stuff, so just the voltage and the battery level. Yes, and you see here 5 days, and you have 95% left, but it wasn't started at 100%. Therefore, you have a little longer runtime. And then I have built something in which on the one side needs improvement, on the other side you need to see this more as a weather forecast, which is changing as closer as you get to the day. So don't take this 600 days too serious. I think if this device runs for 100 days, this number will be much less than 500. So it's really just a silly forecast, but at the end of the power, you get a better forecast. Then we have a lot of other stuff. It's more for the network guys. And in the end, we have this 21 degrees temperature sensor value. So usually all what you see here is you don't need the most of it. You just need the last line. And that shows also that if you once go to production with this, you can also save a lot from that. So next thing, DTLS 1.2 SID for Zephyr. This is also more or less the title of this session. So for Zephyr, it's more common to use Mbed DTLS, and the current version of Mbed DTLS supports SID as well. But in 2022, when I started the project, Mbed TLS wasn't supporting SID. And for that reason, I ported DTLS. First, I ported Tiny DTLS to Zephyr, starting 2022. I used the model as external CFire module. That's okay. So, and it comes with a very tiny footprint, as the name says, Tiny DTLS. It's for tiny. And it's currently a feature branch in the Tiny DTLS project, which supports SID for the client side. We are going to merge, and I have prioritized this feature below some other stuff we need to be more compliant. Okay, so as I already said, though I started the project last year, and Mbed TLS wasn't really at that point providing SID, therefore I choose Tiny DTLS. So Tiny DTLS is an Eclipse project. Here you see the GitHub repository. It's really tiny. It's really tiny. The footprint for the CFire port is something about 24K ROM and 5K RAM. And I guess we can also get rid of some stuff, but yeah, that takes work. And I think even those numbers are pretty good. It supports pre-shared key, and it supports raw public key, and you can use it together with encryption AES 128, CCM, and CCM8. So this is a very common Zephyr suite, and it works pretty well with Eclipse Californium. The good thing for Tiny DTLS, it has a really low platform requirement, so it mainly uses malloc, uptime, random, and then you need to send the UDP messages. And that's it, and you do not have a larger requirements list. The project comes with some build instructions. It's ported also for Riot, and there is a POSIX build. So it's a pretty nice DTLS library, and it works pretty well. So now come to Zephyr. So that's the largest part, I think, in the open source world. So you see there's a project page, there's also a repository. Zephyr is something like Linux for an embedded OS. So it comes with a config system, which is used to configure the build. As some may know from Linux, you enable then that, and then you build your kernel. It has a device tree description language where you can say, oh, I want to have my temperature sensor on E quadrat C and E high 2C, or whatever this is called in English, bus or something like that. And it comes with MCU boot for firmware updates. To be frank, there's too much to say for Zephyr for this session, so I didn't try this. So please use the web. Check out for videos, check out for tutorials. There is so much to say about Zephyr that this would not match into this session. Just a final statement. I think Zephyr uses Mbed TLS, and I think they're pretty happy with this. So I have no plans to make something like Tiny TLS to be really a part of Zephyr. That doesn't make sense for me, but it's an external module and you can use it if you want it. So now we come to the devices. So if you want to use this client with a device, it should be a cellular device, and the cellular device should support Zephyr. Otherwise, it doesn't work out of the box. And as I mentioned already, this modem radio events binding, this is currently only implemented for one modem. This is the Nordic NRF 9160. And on this modem chip, we have two devices supported directly from the project. So the one is the Thinky 91. This works out of the box for first steps. I try to present this here. So this is a really smart stuff. It comes with everything in, battery, cover, case. So pretty cool thing. And then we have also a feather. A feather is a special format. I present it here. It's the version 5, and for me this is really the best in class according to QuiasScan current, and it's also pretty well for custom devices. This means if you want to adapt the Thinky, this is not that easy. If you want to adapt the feather, this works pretty well. You can even have it on a breadboard, and you can easily also use projects for other feathers. So there is not only feather for this modem, feather is also a format where you can buy other processors and other things. So this works pretty well to customize your stuff. The key performance from this software with these devices is what I would like to describe them as. In the last year, we get our experience a mean time between failures from about 8 weeks. This means usually the device runs 8 weeks, but then there was a bug and then you need to interact. So this year we improved this version a lot. And so in our last network outage, all devices with the new version come back without interaction. So I hope that we now have much more weeks than only this 8. The second key performance is then the energy consumption, and I usually measure that at 1 message per hour. And if you run a Thinky 9.1, this has an internal battery with 1,350 milliampere hours. It's a LiPo. Then you have half a year runtime from battery. This means you can charge the device. The device sends you every hour a message, and this runs for half a year. That's a pretty good value. And now if you take the feather in the version 5, and if you use external batteries, and there you then have to use this special low self-discharging ones. There are several vendors who prepare them or who build so low self-discharging batteries. Then my forecast will be 2 years. We will see if we really reach this. Otherwise, even if 1 year is reached or 1.5, I think these are so brilliant values. So let's have a closer look to this NRF 9160 feather in the version 5. In Frederick's session, we have heard something about open source hardware. The feather is also open source hardware, even if it belongs, I think, to another open source hardware organization, but that's still a good development that also hardware goes to open source. It's supported by CFire out of the box. For me, it's simply the best in the class for wildness. This means if you really want to do something outside, this device rocks. So it has the best QuiasScan current with enabled wake up on input. So this means you have a button, you can press this and then it wakes up. That's already takes energy compared to you have no button. But this overall takes only 13 microamperes. Compared to a Thinky, which takes 35, this is already a really brilliant value. I don't know if the newest Thinky is also better, but at least to version 1.5, it was this value. A feather is really easy to customize. This is because of the format. You can put it on a breadboard. You have 3 volts GPIO. This is really much cheaper to add a sensor you want than with everything else I used with this modem. It's also easy to use these low self-discharge rechargeable batteries, and that's really extremely important if you want to have a runtime which is more than half a year or a year, because a LiPo Accu will self-discharge within a year in a significant way. So count about 20%, 25% without doing anything, you will lose that much energy compared to 3%, 5% if you use so low self-discharging batteries. So if we want to use rechargeable batteries, we need to use low self-discharging ones if we want to run for longer than a year. And it's also easier to use better antennas because the antenna of the Thinky is not the best one. It's good enough, but it's not the best. And if you want to use better ones, the feather makes it also possible for you. So this is really my personal favorite for the wild. There's a website for this feather. So it's built by Jared Wolf. It's sold by him. So you can buy someone. You can also buy someone by several distributors, DigiK, and there are also a lot of others. You see on this website a feature list of this feather. You can get documentation, including schematics. There is a cool forum where you get mostly faster answers than somewhere else. And Jared has also YouTube tutorials for Zephyr, a series with a lot of stuff, a lot of informations. That's really great. Yeah, spend some time in watching it and you will get a lot of more ideas what you can do with such a feather. Okay, so now we left the device side, and because mobile network operators usually are not use that much open source, at least I don't know, we can go straight forward to the cloud server box, and this is basically built on Eclipse Californium. So Eclipse Californium is one of the major, co-op DTLS 1.sit implementation. It supports clients and server in mid and large systems. We have a project page. We have also a GitHub repo. It's Java-based and it's native Java, so you can also use it on other processor systems as long as you have a Java there. It's supported to be executed in the cloud. Yeah, okay, that's not that hard. Then it comes with some basic documentation about co-op, the book about the co-op core and about DTLS. I say basic, there is still space for improvement, but at least in the last, the people have been happy with what they can read and what they get as support. It comes with a benchmark client, so if you want to put pressure on the server, you can do this for load tests. It comes also with a very simple user space NUT for communication tests. Means if you want to see what happens if the IP address is changed by a NUT, then you can use this simple NUT, demo NUT, in order to test your stuff. That's also a very great idea. And it comes also with a couple of demo apps. What we also have is a wiki with links to the specifications, with links to external articles, also with links to security-related information. So if you're interested, just go to the wiki and read a couple of those links. And we have also some recommendations how you should install or how you can install Californium. We support so simple and old system D installations for Linux, but it also runs on Docker or runs on Kubernetes. So what you prefer, it's up to you. I already mentioned that we have some co-op cloud demos, some demos, and there some one which I think are pretty useful for the cloud. And there are two. The one is a simple cloud demo server. This demonstrates how you use co-op and DTLS 1.2sit, and it has then enabled graceful DTLS restart. This is a feature where you can update your server and it preserves even the encryption. This means you can do this. I have a setup for Kubernetes where you do this in the hot. So this means you have, say, 10,000 clients. They're shooting about 20 or 40,000 messages per second towards the cloud. And then you can make an green-blue update with Kubernetes, and you will see it works, and you do not really lose a request response, but the client needs to do some retransmissions. But it's then really a very short hiccup. That's a very cool demonstration. And the graceful DTLS restart works now, I think, since 3 years. And in all the time, I only have lost twice the state. So I think this is really pretty cool. It's just a pull request, so it needs to be merged. Yes, there's still work to be done. And the second one is the main thing I would present here, the co-op S3 proxy. This comes also with the graceful restart, and it's right now only a working fork. I just first want to merge this pull request, and then I make the next pull request, and then we have all together. Currently, I have a install script for the cloud demo server. This is using Cloud Init. And I also like to prepare these scripts for the CoAP S3 proxy. With this script, it automatically creates you a cloud VM. It installs then the HTTPS forward, fail to ban, certbot for X509 certificates for the HTTPS stuff, and it installs the cloud demo server. Maybe we remember yesterday about all the security threats. Just to say, sometimes the software industry even makes it without an attack that the stuff is not working, and Cloud Init stopped working yesterday, so I hope it works next week. If you do it now, you will get errors. I'm not even sure if it's Cloud Init or something else, but this is the high-level problem. If you want to have something to say, please install that, regardless of the cloud, and it doesn't work, then it's a work to make it working again. But I think this will be done soon. So what are the common features of these cloud apps? I decided to put all my device credentials just in encrypted files on the local file system, so we don't need a database. Usually you need to read them in, and you need then to have fast access to those credentials. So I think this decision is not that bad. With the CoAP S3 proxy, you can also use S3 to provide those credentials. Therefore, they're encrypted, so we can put an encrypted file on S3, and then the server reads it. The server checks frequently those credential files for changes. This means it frequently checks if the file has changed or S3 has changed. And if so, it automatically reloads the new credentials. We do this for the HTTPS, also for the certificates, and we do this for the device credentials for CoAP S. So that's pretty cool. So you do not really need to worry on or operate on the stuff. This is done automatically. The cloud demo server that comes with a very, very simple HTTPS API to read the last device data. It has no login, and it's really the only intention is to use this really for the very, very first steps. So the intention of the cloud demo server is that you add your own backend to it. And so we have a Java API where you get requests in and you can send responses out. And then you can add your own backend if you really want this. And just if you really want to do extremely very first steps, then you can use also the HTTPS API. So the second one is the CoAP S3 proxy. This stores the device data which you send directly into S3 cloud storage. And then a simple JavaScript web browser app displays this data directly from S3. And you may also use an own backend to exchange data with S3. That's up to you how you want to, if you want to use S3 as exchange or if you want the Java API. I currently plan to release both mid and end of June, so next month. We will see if I can really reach that, or if it takes July, we will see that. So something about the message flow. So the device sends usually the data via CoAP DTLS 1.2, blah, 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 to the cloud server, and it uses cellular radio network for the transmission. So that's the first link. We see this here. So that's the device, that's the link, and that's the proxy. And then this cloud server forwards the data to the cloud storage. You see this here. And this is usually, in many cases, done by a high-speed cloud internal transmission. So if you run the proxy and the S3 on the same cloud, that's usually pretty fast. And in the end, you then have a browser script here on the client, on a PC client, which is then able to visualize the data stored in S3 as text or chart. So the device communication, it's important to know that always the device initiates the communication. After a quiet phase, you need to initiate it again. So this is always a problem. People need to understand the device starts, and if there is a quiet phase, the device needs to start it again. Once the communication is initiated, the cloud server may also send messages back. That's okay. I think we have heard this also for MQTT. In co-op, this is naturally the response. You can also send a request to the device. This takes just a few lines more if you want this, but in many cases, it's pretty good if you have this just as request and response. This works brilliant. So in my experience, you get a pretty good result of all this if you use frequently alive messages. The point is, so I use it every hour. So the point is, usually you have your device and you have your server, but in between there is a lot of other stuff. And if you really want to see that everything is alive and healthy, you need to actually exchange messages. So I do this every hour. So if you have an alarm system and you don't receive a message from your device for 2 hours, then you know at least the system is damaged, maybe also the device is damaged, but you have something, because you would know that it should have reported every hour. So this helps really to monitor the system health, and that's very, very important in such distributed worlds where so many things can be broken. DTLS 1.2 SID helps here to keep the connection costs very low with encryption. So usually the problem of having not too much traffic, but every hour or something like that, is that you have usually a large overhead for encryption, and using DTLS connection ID, this helps a lot to minimize this. S3 service, just for those who are not common to this is a very common cloud storage service provided by many cloud providers. It offers a HTTPS access similar to a local file system, something like list or read or write. It has mappings for many programming languages, and it's even possible if there is no mapping for your programming language, but your programming language offers you an HTTPS client and some crypto function. I think it's mainly the SHA-256 you need. Then you can build also a client on your own. I did this in JavaScript. It was about 400 lines. So now the web browser JavaScript app, which is also implemented within this Californium demo project. This app first requires that you convert something like a username password into a temporary S3 signing key. So S3 security is based on signing keys and on API keys, and you derive from the API key the signing key. And so this derive function is implemented in an HTTPS service, and this is included in the co-op S3 proxy. You can also use split it and implement it somewhere else, but that's needed. Therefore, we also need this X509 certificate only for this HTTPS. Once you have this signing key, then you can communicate direct with the S3 HTTPS API. You can then call list files, read files, and write files. That works wonderful. And the only benefit of all this is that it really comes with extremely low cost. So this is this serverless stuff. For serverless stuff, you only really pay what you do. So for many projects, if you use S3 and you can use this directly as your API for your web browser client, this reduces the costs very much. So is really a great effort there. But okay, this has a downside. It's limited. It doesn't directly support fully featured applications with sophisticated user management, especially sophisticated user management. It's not the strength of this approach. It's more like you can have a group which has the permission and the others don't have the permission, but it's not building up special groups or something like that. This is not the intention. So if you want, you have here the link for the app. It's a pretty simple one. It's 1,500 lines. This includes the login and the S3 access, and you can see how it calculates the charts. Yep. So here again, something just to clarify. So the first request is sent to the proxy that converts the username password to the S3 signing key. And then with the S3 signing key, we directly access the S3 storage, and then we either display the text or we calculate a graph, a chart. So cost considerations, I already mentioned this. So devices starting from €5, this could be read. So there are people who say, yes, the devices started at €5. For me, this seems to be rather unrealistic. I haven't seen such devices. For me, in my experience, devices for cellular, that's also the point, it's a cellular device, they're starting about 40 to 50 euros, but that's are really the cheapest ones. And for a customized device, when you put your own sensors and some stuff like that, then my experience is that this device will be closer to 200 euro than to the 40 euros. So that's really, so the price for the device is really the problem right now. A feather itself, so this this small thing here, it's about $100, and the price for the Thinky, we have this here, it's about $126. So you see, the device is really one of the major cost points. The device has usually a SIM card, as you know from your cellular phone, from your mobile phone, and you need to pay for this SIM card. And it depends a lot on what you want to do and where in the world you live. So some providers offers you cellular connectivity starting from €1 per year, and others from €1 per month. Mainly you get not too much data volume for this €1. It's then about 50 megabytes a year, so 50 megabytes, not more. So you cannot run your PC or something like that, but for a cellular modem, that's okay. For a cloud VM, you need Californium, should run at least 2 gigabyte RAM. That's because the Linux and the GVM footprint is already about 700 megabyte. So usually a medium-sized VM does it. That's about 20 to 80 euros per month. This depends on the cloud you run on. And the number of possible devices depends a lot on the communication pattern. So again, I usually use this 1 message per hour. And with that calculation, a medium-sized VM can actually handle 100,000 clients. That results in about 30 requests per second. This cloud instance will be also able to handle, say, 400 or 500 or whatever requests per second. It's mainly limited by your S3 storage. Without S3, it's no problem to handle 10,000 requests per second. Anyway, if you have just a simple JavaScript app, I don't think that you can handle that many devices. I think it's more realistic to think about 1,000 devices or 100 or something like that. And sure, for those who want to use it in large scale, if you have more RAM, say 16 gigabyte and 4 cores, maybe a dedicated VM, it's no problem to run 1 million devices. And we have also heard in the session from Kai and Hono that he runs 1.5 million devices. That's okay. I think maybe, Kai, you can also post how much this costs you per month in the cloud, because I think if you consider just to use Californium for that, I guess the numbers will be much, much, much smaller. At least that's what I think. So my S3, so S3 comes also with costs. The point is it's very low. So in my usage of the last 9 months have just been always below 1 cent. So I haven't paid even 1 cent for S3 because my usage was always too small. Let's see if that's changing. So what's about your first steps? I hope that you get curious about all those open source projects and how they fit together. So for really very, very first thing, we have pre-compiled binaries for the Thinky and for the Feather. And if you put them on the device, Then you send the data to the Californium sandbox, and then you just need a co-op browser or client to see your data. But it's really just a very first thing for those who are just curious and who want to see if cellular modem is really that power efficient or not. If you then want to do more, you need to install the Seafire toolchain and start to build your own apps. And I hope this is then mid of June, end of June. Then we will have all install scripts ready for the cloud VM. Then you can set up your own cloud box. And then you just need to redirect your device to your own cloud. Basically means that you make a build of your device and you then enter your cloud server as destination. And then you're ready. Then you have your own cloud set up. So my personal conclusion, yes, once open source is integrated, it's really a pleasure to use it, and it provides really exciting possibilities. So it depends on who you show this thinky example. So one can do nothing with it, and others get ideas. And I hope those who get ideas, they see in this setup also a possibility to get more into the real world experience. I know that other solutions come with more UI, come with more device management and so on. That's not a point. I think just if you keep in mind, this is mainly the focus is on having a real world device with real communication running from a real battery and really for weeks and months. That's what this project should demonstrate and show you. Then I would say just compare this solution with others in the wild and not with solution papers, because on papers you can write a lot, in the wild you get less. So that's it. I hope some are awake and not everybody fell asleep.
Not at all. Everyone seems to be awake. We do have a question. We actually have two questions. One from Vikram. What does co-op-c3 proxy do? Sorry, I misspelled that.
Okay.
I see. Thanks. That's what. Okay. I think you answered.
Yes. So it's Vikram. Vikram, this is. I think you was the one who rescued the co-op proxy functionality years ago, and principally, this is nothing else. So when you have co-op, it's converted to HTTP, and now it's converted to HTTP directly forwarded to S3. So S3 is a file system like a hard disk. You make on the file system ls, cat, echo, or something like that, and S3 just writes the data from the co-op request into the S3 storage. That's it. I hope this explains it. And it's just like something like you take co-op, you make HTTPS, and with HTTPS, you just forward to the S3 stuff, to the S3 service. So that's really, really easy. Okay.
Awesome. And then we do have another question here. It's how hard would it be to use a different RTOS than Zephyr?
For tiny DTLS, that's absolutely no problem because it's also ported to other real-time OS. That's not a point. The tricky thing is that any communication transmission technology, except those ones who are always connected and always using power, because if you have always power, then everything is okay. But if you're not that, and if you use something like cellular or something else, then it's always that you have a transmission layer and that the above protocol makes assumption about this transmission layer. And to exactly forward that information from the transmission layer into your protocol layer, in say, as I made an example, in order to start the retransmission timer really at the right point and not at the wrong one, therefore, you need hooks and other stuff. And I'm not sure how does this then deal with other RTOS. So the point is also not, I would even say the point is not the real-time operation system. The point is more the device and the communications that you're using. If you have that, then you can do it. And yeah, so I hope this answers somehow, because a different RTOS can mean a lot. And the project is more about a cellular device running a co-op co-op over UDP or co-op DTLS over UDP. So on every system you have this, it should be possible. Maybe it took me 2 afternoons to get it initially working on Zephyr. So Tiny DLS working on Zephyr was 2 afternoons. Make it really as external modules was then a couple of weeks, but that's something else.
Okay, and then we did have another question in the chat, or more so a statement, but where is it used in field or automotive? Temperature, sensor, ... That's from Badi.
To be frank, currently there are 20 devices using it, and the most of these devices are here in my office. And so it just starts up. So we have just now the first interesting people who want to have a look on this. And yeah, I think that the question would be otherwise, where is Californium used? This is something else, because my session is about the Finky and about this modem stuff and about the Californium S3 proxy. But I think in general, if you ask where is Californium used, then you can use Shodan IO, and then you see it's about, I think, 200,000 servers in the world. But as far as I know, about 1,500 ThinkBoards server and 800 Legions and 1,000 Californium servers. So around about 3,000 cloud servers which are using Californium. And I don't know which industry is using it.
Okay. All right. I think that's it for questions. What a great presentation. Thank you so much again for joining us. And we hope to have you again next year if we do the virtual IoT and Edge Days. So thank you, everyone. And just a final reminder again for the 2023 IoT and Edge Developer and Adoption survey. If you could take some time to do that and help us out, that would be greatly appreciated. We'll be back at 2:15 with Kilton Hopkins. Thank you.
Bye.
Hello, Kilton. Welcome to
Thank
Virtual
you.
IoT and Edge Days number 2. We
very
are
much.
excited to have you. You're so welcome. So let us know when you're ready to go, and you can start sharing the screen.
Okay, great. I'm going to start sharing right now.
Perfect.
And you can tell me if that has come up.
Absolutely. It looks great.
Excellent.
Over to you.
Thank you very much. Good morning and afternoon and evening to everybody out there. So we'll probably need every minute of the time allotted here for this presentation. And although I'll try to save 5 minutes at the end for questions. And so given that, let's go ahead and dive in. There may be some parts of this that will be rather dense. That is by design. There's a lot of information packed in here. So what we are going to talk about is edge native architecture, the concept of a modular approach. So off we go. Now, why have we been working in the open on edge computing architecture? Why do we want an open source edge? Well, some of the key reasons and some of the typical reasons we do things in open source, but interoperability between systems is a major concern. And there's not really a way to foster that if you have closed source code base. And there are some parts of edge computing that are so mission critical that we would all be better off if there was a smaller code base made more robust by a lot of different parties working with it and putting it through a lot of different challenges. And ultimately, I think infrastructure freedom of choice is something that we've pretty much all decided on. We prefer this in cloud environments, and we would prefer this in edge environments as well. And so having it be open gives the opportunity to keep that in place. And we are definitely smarter together. So as everyone brings their area of specialization, their years of experience or months even of experience, every contribution helps define how edge computing should actually go. And then in an open architecture, we have the opportunity to take in and hear the voices of all stakeholders. Much more difficult to do when it's something closed and operated by a single organization, which would probably favor serving its specific customers above and beyond anything else. So that's why we do it. Why haven't we seen edge computing solidify the way that we would like? Well, so let's get real about open edge infrastructure and some of the challenges that seem to be perhaps unique, at least more influential in this circumstance than in other aspects of computing. So the vendor business incentives are important. This is not that vendor business incentives are a problem, but when you think about it, the incentive to gather the edge and IoT data along with providing the edge and IoT functionality, yeah, that makes sense because having the data flow through your system is good for business. Now, that doesn't mean that that can't be the case, but that is actually pulling in the opposite direction of having a unified open edge architecture because everyone would want to have a place to hold the value that's flowing through the system. Okay, there's got to be some way to work this out, but that I see that as an inhibitor. And there's a time frame mismatch. The amount of work needed to handle the heterogeneity of edge environments is showing that perhaps the grand goals are farther out than we had thought if we're going to do it right. Okay, well, that would mean that we'd be moving step by step toward a nice, robust, unified open edge architecture. And we need to take that into account and manage the hype. Well, I think we are no longer in a super hyped edge computing marketing environment, but there are maybe some expectations that have gotten ahead of what the reliability of systems might be ready to achieve. And that taken into proper consideration would mean that it's evident that there's still some work to be done. So that would help understanding the time frame mismatch. Now, usually early stage software on maybe the application side, it results in a couple of iterations, some early learnings, and then we finally land on something that is production scalable, stable. When it comes to infrastructure, early stage attempts can produce some legacy hangover even prior to mass adoption. There's just simply a lot of work required to make the components come together and interoperate, make a whole edge computing system. So you're going to want to avoid rewriting things that are good enough, but then you're always carrying stuff forward. Well, this is fine if it's in the course of a year, but what if it's in the course of 5 or 6 years? That's a lot to have to move away from. So even prior to major adoption, you can have legacy concerns. And to a good extent, the true requirements of edge computing only surface when it's stress tested. And so as we go along, new requirements surface and then fall back on that legacy code base problem, and the incentives to rewrite a system, it has to align with somebody's business goals or career goals, whatever it might be, and the time available. There's an allegiance to groups that's always a part of any open source effort. And that itself is not a problem, but we are not yet in a stage of edge computing in which I think that there should be factions. We haven't arrived yet. And so collaboration, I think, is greater than perspectives and opinions still at this time. And then, of course, there is the marketing that goes along with any computing industry theme, or call it computing industry wave. And when marketing gets out ahead of the state of that computing wave, it can produce so much confusion that it's impossible to get any attention for something that actually does need some pilot usage or trial runs, or perhaps early production usage. Everything seems to have every feature on day one when a hype cycle ensues, and that actually ruins the market forces that are normally supposed to shape how technology develops. So yeah, I think that was a hindrance, and I think it's been a hindrance for IoT and for Edge, and I fear it's happening again, and it's happening for AI. So the marketing blanket of confusion is a serious inhibitor of real progress. Let's get down into, though, the modular approach and edge computing architecture, and where I think we can head. So we've learned a lesson over time that I think holds up for Edge as well as it's holding up for cloud. And that is, we seem to prefer a few ways to do things per layer of functionality. And the layer in display here, you could say, would be how to handle artifacts such as container images, or the binaries that are intended to run on a more constrained device. And so if artifacts and artifact management is the layer we're talking about, here we have just a simple diagram of 3 equally good choices, and all of them will fit the bill, but how you do it depends on what you need from the system. So the theme here is we tend to prefer having a more than even, one or two ways of doing things that are satisfactory, so that we can have each approach be good at the way it does it and useful for certain scenarios. And while 3, 4, maybe even 5 are good, 18 is not, because you lack the robustness and you lack the sufficient market share or usage share that you would get if instead of 18 we were at 3 or 4. So keeping this in mind, we should consolidate wherever we have repeat functionality that is not differentiated enough to justify being its own approach to a layer. We'll talk about layers. We'll get into what those layers are here. But so when I say modular, what do I mean? Well, you can still compile a binary, and so I chose the edge compute agent, which is a common part of edge architecture. I'll go through the edge architecture layers here just after this. So the edge agent is it's pretty much the established paradigm in edge architecture. It's the software that runs on the edge compute node that does the management of and execution of the workload. And this is so common that there are agents for all types of systems, including a tiny agent that will report back the health stats, the resource usage stats of an edge compute node, separate from the different agent that works with the container runtime and so on and so forth. And so, since this is an established pattern, I thought a really good way to describe what modular means is to talk about the agent software, because it would be a point of contention normally for modularity. That's because you need to compile it, and you don't want to deploy 3, 4, 5, or anything more than one, ideally, edge compute agent. And perhaps it loads other stuff, but the best would be to actually have the ability to choose what components make an edge compute agent that would suit your system needs. And then once it's built, can reliably be deployed as a single package, a single binary, to the various devices that you care about. So you may only build it for one architecture, for example, one CPU architecture, if that's all you're going to need. It does not need to be assembled from independent running binaries. So this also means that version control and all of those things about managing in the edge infrastructure become a lot easier. Well, if we're going to build this thing and compile a single binary, how on earth could we make that modular? Well, one example of this here is to break out what is core functional, and therefore you must have one of those choices included, and those are in blue. I'll show some examples after a few more slides of what those core functional threads should be, or what they have shaken out to be in, I would say, kind of like common edge architecture examples that have accumulated. In the green is the notion of choosing a pre-made extension for the various pieces of functionality you need in the agent. But any number of these can be included, but are not strictly necessary for that agent to do its work. And here I've given some examples such as a chosen storage extension or a data plane extension, monitoring extension. These could be open source or closed, third party. I guess if closed, you would need to be provided a module that can be included in the binary, so a little trickier. But let's say they're all open, every one of them. You grab these components, and then there would be functionality for how to compile and then distribute the agent binary. But you don't have to write these. It's probably going to be the case that there will be an extension provided by all of the major vendors for interfacing with whatever products that they provide that you want to tap into. An example would be an artifact registry. And in choosing that vendor, you would have available the agent extension that you can use in building your well-fitted kind of, you could even say, tailored or made to fit agent. And then in the orange is the notion of a completely custom extension. This is where extensibility and modularity they go hand in hand. And it's an example of how to get around the problem that we are facing in edge computing of needing to provide some kind of a custom handler for scenarios that arise, perhaps were unpredictable at the onset of some system planning, but situations arise and we need to build some custom functionality to make the whole thing actually work. And one of the most important ones is being able to use non-CPU silicon, non-CPU processing resources, such as a GPU or any form of AI accelerator silicon that is attached to the edge compute node. And so rather than try to cover the entire world or be limited to just one or two of the most common options in a code base, it would be best to have extensibility be the focus, and with modularity, then you could independently develop that extension and any number of extensions, and then build those in. So worth noting that if we're talking about a piece of agent software going on an edge compute node, we should define real quick what an edge compute node is, and that's simple. Any hardware that is capable of running arbitrary compute workloads, and therefore probably has a genuine operating system, it can be called an edge compute node, provided that it attaches to some control plane in order to receive its compute instructions, and does not only make its compute decisions locally. That would probably be a pretty fair definition. So wide range of hardware, wide range of locations. There is no particular edge, and there is no such thing as specific edge compute hardware, although such a thing may develop and have a definition at some point, not one that I can see now. So we're at a point, I think, that enough patterns have emerged that we can start talking about what seems to have landed as and settled. And so for this slide and the two after it, I will walk through some patterns that, to me anyhow, are evident and probably don't need to change, just need to be leaned into a bit more. So the first one is I have yet to see any controller for edge computing that isn't at least beginning with a central point of contact that all of the edge compute nodes can rely upon. Now, I put central-ish because it doesn't really matter if you start with, let's say 5 redundant controllers that the edge compute nodes can choose from, maybe geographically distributed or just for load balancing, doesn't really matter. And it doesn't, as I was saying, it doesn't matter if that's how things begin, is start up with those 5 and then get handed off to a mesh or a peer-to-peer system or anything, you could even say, decentral. But central-ish is what I see everywhere. And that makes sense to me because you need to protect the control plane. And while there are ways of protecting things deeply as they go far afield and have no ability to be directly controlled, it is far easier to have protection and control over this part of the system by following patterns that we already have for other types of control planes. So, i.e., a cloud or similar to cloud, so data center, some centralized hosted controller that then can take the edge compute nodes to some other control plane connection, but it begins this way. And I'm a-okay leaning into that architecturally. I think that makes a lot of sense. And I already covered this one, but there's an agent per edge compute node. And I don't see any reason why agent on one compute node should sub-orchestrate or perform the role of controller down to other edge compute nodes. Perhaps there's environments in which that would be good, but basically you have a piece of hardware, you put agent on it, and then you have an edge compute node, and they're all equivalent. They all operate the same, and everything after that is part of what that agent does. Artifact sources are not what's what I'm looking for here, are not a rigid or fixed definition. They are not an opinion of the edge compute architecture. They should be configurable. And that's so that there's no hosted registry of containers or something that is the only place that you can draw from. It is mixed sources that has become apparent, and perhaps even different types of artifacts for different types of workloads. And so going with that, it's also a pattern to allow mixed runtimes if possible. Now, this is more of an emergent pattern, but for years, it's already been a point of discussion how to allow a variety of runtimes in the same edge compute infrastructure. Examples of runtimes, if you don't spend a lot of time in the space, would be Linux kernel container environments, runtimes, and virtual machines or WebAssembly. You can even take it down to an executable binary that just needs to have the proper signature and verification before it's included in a running application and allowed to execute. With the variety and the addressing mixed runtimes in the core architecture, we get away from the kind of vendor-driven stack issue and allow for genuine flexibility. We'll take a look at what it would be like to have multiple runtimes and still have a universal code base that's modular. So another pattern, really important one, is a separate data plane. Separate meaning it's separate from the control plane. Having the ability to contact an edge compute node from your controller, give it new instructions, see its status, etc., that does not need to be tied to the flow of data coming from the workloads on that edge compute node. And having the two be separate allows for innovation in both spaces. Having them tied together, that means that you have a limited number of use cases that you can address with that architecture. And you also have a limited number of users because there are concerns over where data flows. And the control plane is net new in this scenario. So why would you want to have to drag someone into a new data plane or retrofit your control plane into where they're comfortable with their data flowing? It would make sense to keep them separate. So other patterns, infrastructure as code is dominant, and for good reason. You would certainly want to be able to lay out a fresh edge computing environment based on the work that was done for the last one. And you would also want some control over how those environments get stood up and all of the little details. Infrastructure as code wins. Stick with it. I don't think there's anybody would argue that that's the right pattern here. Mixed CPU architectures. If you've done anything with Edge or IoT, you probably know that ARM32 and ARM64 and smaller x86 devices, standard rack server x86 devices, they're all in the mix. And that means that right off the bat, Edge native architecture needs to address the mixed CPU architectures that it will be issuing workloads to. And if that's an afterthought, it is painful. And some of that legacy effect or hangover effect of early code base, that is this is one of the areas where it's been fit in after the fact, and makes it much more difficult to scale. How would you extend? How do you do the build path for the workloads? And much better if it's in there from the start. This next one is, I think, very important, because there are a lot of things out there that work really well if you can get all of the workloads, so all of the application microservices, if you can get them to be built with some SDK or some tie-in to the control plane or the data plane. And the uptake on that is far lower than when existing applications in their state that they're in already, in the cloud, can be deployed onto the edge computing infrastructure directly. So what's emerged as a pattern that, at least the way I see it, is having applications need some build or some compilation that attaches to edge computing infrastructure is less desirable and should be avoided. Now, when evaluating an edge compute node for its health or its ability to handle a certain workload, you have to look at its available resources. And that's not just RAM, disk, and CPU. We're talking, does it have a GPU for accelerating the AI? Does it have a camera attached to it, because this is a computer vision workload? So having common resource identifiers makes orchestration possible. I would say makes universal orchestration possible. And so that pattern is a newer one, common resource identifiers, and an area of that I'm personally keenly interested in, because without common resource identifiers, every system has to implement some form of translation, or even worse, every system has custom passing of resource identifiers that it's defined, and is basically just locked into its own stack. So extensible orchestration, this pattern means we have orchestration that is edge native, but it doesn't try to contain algorithms for every scenario, but rather has some really solid root orchestration functionality oriented around edge, but can be extended to include additional rules or algorithms, and how it makes its decisions. Edge orchestration is so vastly different from cloud orchestration that although the patterns that exist in the wonderful orchestration inside the cloud native stuff, and it's Kubernetes, well, although that is a wonderful model, I personally feel that without the right approach to using that as the base, it would probably be better to have an edge native core orchestration. Not saying it has to even be a different code base, but this has to happen at the core, because the very nature of edge orchestration is different. You could, of course, have an interpreter anyway, that's the topic for another time. So we also need to finish out defining edge primitives in a way that those data structures can be relied upon. Now, there's a lot of work in this area, especially when it comes to defining workloads over particular protocols. See Eclipse Sparkplug, for example, good stuff. What we want is to know, how do we define some of the pieces of data that are really important to edge computing, and we really only want to get them right and then move on, because this is where system interoperability can happen, and it's blocked by the circumstances in which we just kind of define for ourselves the order of the coordinates, latitude and longitude for location, as an example, as I put it on the slide here. If it's not all done the same way, then extra work is required, and all of those little bits of extra work add up, and then siloed stacks are preferred. So let's not do that. Okay, last bit here on the architecture patterns. So standards also for monitoring and metrics. What defines the resource usage on an edge compute node, and what types of metrics are the norm? So I would definitely prefer to look across edge computing infrastructure and see the same types of measurements so that I can compare apples to apples, as they say. And so I think we have yet to really see standards that are refined for edge, but there's a whole bunch of examples out there. So perhaps it's a matter of just aggregating what is in the field, but that's important. Identity management should be separate from even the control plane and the whatever code base the controller or comprises the controller. And that's because identity management often extends outside of the edge computing infrastructure. It may touch on the manufacturing of hardware, like of actual devices. And so if we have separate identity management and then all of the right hooks in between the different edge architecture components, it's possible to leverage existing systems, buy from existing vendors, follow the process of embedding an identity into a device that is ready then to connect to your chosen control plane. And so better just to do identity stuff well by doing it separate. Compatibility with cloud components, what I mean here is more than just kind of the, I would say, self-evident compatibility of being able to upload something to storage, cloud storage, like an S3 bucket, right? It's aside from that stuff. What I mean here is there are cloud and cloud native components that could be included in the edge infrastructure as long as they are given the proper carve out. I don't know why we would want some new component for doing the front end security and DDoS protection, for example, for an application that is hosted on edge compute nodes. It shouldn't have to be invented again. So how do we make sure that that's compatible? It would be a huge step forward, and that there would be a lot less that needs to be done to make edge viable for the level of scale we're aiming for. And I put here multiple tiers of security approaches. What I mean by this is there are some scenarios in which we have to have the deepest, most reliable top-level security for perhaps the edge compute node itself, right? The edge device. And other scenarios where we really don't care that much. It is 100% internal. Perhaps the device is used in a facility that has enough security that the last thing we would ever be concerned about is that edge device being compromised, as it's maybe in a location where you would have to compromise so much other stuff to get there. In those scenarios, we don't need to follow one security approach, but rather have options. And that has kind of proven to be the case. And everyone also wants to start their earliest work with the lowest amount of hurdles to get over. And frequently the security of devices and complexity of provisioning for production, those things stand in the way of developing a working system, which is, of course, the only reason you would even bear those costs, is you have something worth putting out there, right? So how do you facilitate that? Okay, and being workload acceleration aware, I think that is has emerged as a pattern that it deserves to be a top part of edge architecture. Right from the start, I think the way that edge compute nodes are included, it should have a listing of what workload acceleration is available, so that they can be part of workload acceleration aware orchestration. And it's just another aspect of edge computing that is, I think, a bit more prominent in edge than cloud, but I could be wrong about that. But I think a lot of edge use cases lean on being able to do real-time processing of things. So there you go. And final, and I highlighted in yellow because it's the topic of the talk. I think we've seen enough code base now for edge computing to identify that the parts of one, which are excellent, would be really great to merge in with parts of another, where that other bit of code does some particular things well. Have to be extensible if modular, and I think having reusable edge native components with extensibility can allow for achievement of things we're looking for. So cool. So in the few minutes remaining before I leave some time for questions, let's look at the specifics of an edge agent. What would a modular edge agent look like? Now, you just assume here the yellow box, and then within it compiled agent binary. Just assume that the tooling works, that these things can be compiled together, that you can distribute and run that binary on your edge compute nodes. What's inside it is what's important here for the talk. So the upper left, this blue one there, part of the core, right? If you recall from the earlier slide, core thread functionality here is in blue. Something has to be the application and know at the top level, I'm running or not running. There should not be any blend of main threads, meaning that there should be no processes that run independent without something at least starting and stopping them that can be called the main. So then below that, the next couple, control plane command executor. This is a module that can exist on its own. You can write this code and have it be a piece of software that works properly without being attached to anything else. What that control plane command interface looks like, that's something that needs to be determined. But for any given commands arriving at this piece of code, this little module can carry out and monitor and track the progress of instructions. We'll see in just a moment what it might do with some of those instructions. Beneath that, connection broker, if you have a module that is an entirely self-embodied piece of code and its job is to know that it has a given identity as it gets passed and everything, its job is to know that it has a reliable verified connection to its designated controller or control plane, then this code module can do its job really well and be built into the agent, but could be extended, modified, or configured, right? So it's much easier to write a configurable one that only does a certain scope of functionality. Could be configured to attach to different control planes and understand how to broker and verify the connection. And then perhaps it'll be a common interface with the rest of the components to say connections live, right? And that might be a common event message that could be used to pass between them. There's a lot of different ways to do this. So the next blue stack, runtime interface. This would be the thing that talks to the Docker API, for example, and knows how to start, stop containers, get the stats, and cause a restart or whatever it is. Open a port with that container. All of these things are built into that runtime interface, and with a separate code module here. You could say I'll include the one that does the virtual machines and WebAssembly. I just don't need any other stuff, and have that included in your agent binary, where the instructions that it receives from the middle one on the left, the command executor, the instructions it receives to start, stop microservice, right, or workload, it knows how to then make that happen. And it's going to lean on artifacts being available, one right beneath it, an artifact handler. It seems like a separated area of concern to know via the command executor which artifacts are now need to be added to its handling, and it'll go do its work. So we go so on and so forth through these. I'll be a little faster with the rest of them. You have a component for storage. Handles all of that. It does it really well. Can be the focus of the work of some people who really understand it, and seal it off as a complete unit. Can be separately tested. Same with Identity Manager. These are concepts of modular code. The green here, we've got some interesting ones. Resource Scout. This piece of code exclusively looks on the network and the local machine and everywhere in its purview to find what resources are actually usable by this edge compute node. And then, of course, we'd want to put them into a standard description. Health monitoring, active security monitoring, which could include AI. There's all kinds of ways to do this. Log management, and then standard off-the-shelf device interface, and metering on the right in the yellowish orange here. An AI accelerator chip interface, custom, designed to work with a particular AI accelerator that perhaps is just getting its market traction and would a nice extension to plug into the compiled agent here, or perhaps an interface for a particular camera that is attached to the edge compute node, whether it be via USB or network. This interface extension would allow the agent binary to have natural control messages turn into actual device instructions, right? And this is an area of challenge for so much edge computing, ends up being application components to drive devices, which is not ideal because then you'll end up with a whole bunch of application microservices to talk to every permutation of device you might find. And so it's got to be a better way. All right. So just some standard interfaces real quick. We're going to need, we always have needed, and I would say to do any of this right, we're going to need now standard interfaces, and this list can go on, but yeah, what are those standard resource definitions for edge resources? How would you specify a workload that's above runtime details? It's a superset, but in some ways, and a subset in others, right? It needs to be extended. What are the edge computing primitives? Things like a location, just nail them down if they aren't. And then, example would be, what's an event message catalog, where the messages can be carried any which way, but our messages about the edge compute infrastructure. And this is, a way that you might segment off a low bandwidth, poorly performing part of your data plane and route things elsewhere. But if these messages aren't defined, then every implementation is different. And I don't know if we're going to get where we want to get. So last here, just notes on why I have spent so much time with edge computing and will continue to. Edge computing is the first distributed computing that is not bound by this mandate to take over hosting existing application stuff and system stuff. And so since it doesn't need to, this is not supposed to be the replacement for some massive e-commerce site, right? Edge computing is net new in so many ways. That's really important because it gives it the breathing room to be different. And this is our second shot at applications over the internet, and we've learned a lot, so we get a chance to do it right, do it different if needed. And the repercussions go back to the cloud. What gets figured out in edge computing can help everywhere. Edge computing operates under the most extreme conditions, so if you can get it right for those, that's good progress. And if edge computing is truly done edge native, the only assumption is that it can actually operate on top of a reliable functioning operating system. Doesn't assume connectivity or anything like that. And so in other words, it's able to handle itself under adverse conditions. So these are things that are exciting, reasons make it worth doing. So that's it for me, and it looks like I'm right on time, but I can stick around and answer questions via the chat if desired.
Amazing. Thank you so much, Kilton. That was awesome. You have it down packed right down to 3 o'clock. So I don't have any questions in the chat, and we'll just have a quick look at the Ask a Questions tab, and nothing there. Nope. So that's it. Yeah. Oh, actually, one just came in. Amazing. From Frédéric. It's intriguing vision, Kilton. Where should I go if I want to participate in this vision?
You should join the effort that will be rising at the Edge Native group at Eclipse Foundation, and there'll be some starting modular components as new projects over there very soon, and that would be a great place to get involved with building out code base, helping with specification. Yep, and to express interest, you can just contact me or go to the edgenative.eclipse.org. That's a good place to start.
Amazing. Well, this concludes day 2 of Virtual IoT and Edge Days. A big thank you to all of our keynotes, our speakers, our attendees, the community, and the Eclipse Foundation team for making this event happen. We look forward to Virtual IoT and Edge Days 2024. And we'll be sharing the past 2 days with all of you on our YouTube channel, so be sure to check that out. It should be posted by the end of this week. So again, thank you, everyone, and go do that survey if you haven't done so already. Take care. Bye for now.